Welcome back. Tonight we're drifting through the ancient pathways of comets, those wandering messengers from the edge of everything, carrying frozen secrets older than the Earth itself. If you're new here, consider subscribing to join us on these quiet journeys through the cosmos. Now, let's begin. You might have heard comets described as dirty snowballs, and while that sounds almost dismissive, like calling the ocean a puddle, there's something beautifully humble about it, because that's essentially what they are. Chunks of ice, dust and frozen gases clumped together in what we call a nucleus. But here's the thing that makes you pause. Most comet nuclei are only a few kilometers across. Some are smaller than the city you live in, smaller than the distance you might drive to work. You could walk around one in an afternoon if the lack of gravity and the vacuum of space weren't, immediately fatal. And yet from these tiny frozen cores, these cosmic pebbles really, springtails that stretch for millions of kilometers, millions. Picture standing in your backyard and unfurling a ribbon that reaches past the moon, past Mars, stretching so far into space that light itself would take minutes to travel its length. All of that spectacle, all of that cosmic drama, emanating from something you could fit inside a small town. It's a bit like watching a single snowflake create an avalanche, except the avalanche is made of light and ancient ice, and it's happening in the absolute silence of space. When you look at a comet blazing across the night sky, you're watching something impossibly small announce itself to the universe with impossible grandeur. Maybe that's what makes them so mesmerizing. Not their size, but their audacity. These fragments of the solar system's birth, these remnants of creation itself, refuse to drift quietly through the darkness. Instead, they grow magnificent tails and demand to be seen, proving that even the smallest things, given the right conditions, can shine across millions of kilometers of empty space. The ancient Greeks looked up at these strange visitors and called them comets, which means long-haired star, and you can almost feel what they were seeing, can't you? Imagine standing in an olive grove 2,000 years ago, no light pollution, no city glow, just the pure darkness of night, and there, among the fixed, predictable stars, appears something different, something with hair, something that looks like a star decided to grow flowing locks and drift across the heavens like it was caught in a celestial breeze. It's such a human impulse, isn't it? To see something unfamiliar and describe it through something familiar. They didn't have telescopes. They didn't know about ice and dust and solar wind. They just saw what looked like stars with beautiful flowing hair, and so that's what they called them. Long-haired stars. There's something almost tender about that description, something poetic that our modern, dirty snowball terminology, accurate as it is, can never quite capture. And perhaps they weren't entirely wrong. Because when you think about it, a comet's tail does behave like hair in wind. Not air wind, but solar wind streaming out behind as the comet moves. The Greeks were observing something true about the nature of these objects, even if they couldn't have explained the physics. They noticed that these weren't just points of light, these were objects with flow, with movement, with something trailing behind them like the hair of someone running through an eternal darkness. 2,000 years later, we've kept their word. We call them comets, carrying forward that ancient Greek observation, that moment when someone looked up and thought, that star has grown hair. Sometimes our ancestors, working only with their eyes and their imagination, found poetry that contained truth. Here's something that seems to break all intuition. A comet's tail always points away from the sun. regardless of which direction the comet is actually travelling. Read that again because it's stranger than it sounds. You'd expect a comet's tail to trail behind it like the exhaust from a rocket or the wake of a boat cutting through water. That's how tails work in our everyday experience, right? Movement creates direction, and things get left behind in the opposite direction. But comets don't follow those rules. A comet approaching the sun has its tail pointing away from the sun, which makes sense. Sure, it's streaming behind. But then, here's the beautiful strangeness. When that same comet swings around the sun and heads back out into the darkness, its tail continues pointing away from the sun, which means the comet is now travelling tail first, like a car driving backward down the highway, except the car is moving at tens of thousands of kilometers per hour through the vacuum of space. The tail isn't created by the comet's movement at all. It's pushed, actually physically pushed, by solar wind and radiation pressure. The sun is essentially blowing the comet's vaporizing material away like dandelion seeds scattering in a breeze, except this breeze is made of charged particles and light itself, and it's powerful enough to push dust and gas across millions of kilometers. The comet doesn't choose where its tail goes. The sun decides, radiating outward in all directions, and whatever material the comet is losing simply has no choice but to stream away from that overwhelming solar presence. So you get this counterintuitive image, a comet fleeing back toward the outer solar system, rushing away from the warmth and light, but its tail is leading the way, pointing ahead like a cosmic windsock showing which direction the solar wind is blowing from. It's one of those beautiful reminders that space doesn't care about our earthly intuitions about how things should move. Out there, in the darkness between worlds, different rules apply, and sometimes objects travel backward through the cosmos, wearing their tails like flags that always point away from the sun. But wait, there's more to the tail story, because comets are overachievers when it comes to cosmic spectacle. They don't just have one tail, they have two distinct tails, and they often point in slightly different directions like a fork splitting the darkness. There's the dust tail and the ion tail, and each one tells a different story about what's happening to the comet as it's being simultaneously destroyed and revealed by the sun's energy. The dust tail is made of, well, dust. Solid particles that have been freed from the comet's nucleus as ice vaporizes. These particles are small, but they have mass, and that mass means they're affected by the comet's orbital motion. So the dust tail curves gently, following the comet's path like a soft glowing arc. It's usually the broader, more diffuse tail, coloured slightly yellow or white from reflected sunlight, and it sweeps behind the comet in this graceful, gradual curve. Think of it like sand spilling from a moving truck. The particles spread out along the path of travel, creating a curved trail. The ion tail is different. It's made of gas, molecules that have been ionized by solar radiation, stripped of electrons and turned into electrically charged plasma. And here's where it gets interesting. This ionized gas is so responsive to the solar wind's magnetic field that it streams almost perfectly straight back from the sun. While the dust tail curves, the ion tail points like an arrow, usually glowing blue from the ionized gases, creating this striking contrast in colour and shape. It's narrower, straighter, more urgent looking somehow. So when you see a comet with its full glory on display, you're actually seeing two different tails created by two different processes, each responding to different forces, splitting the night sky with this delicate cosmic fork. The dust tail curves gently, remembering the comet's journey, while the ion tail points straight back, a perfect indicator of the solar wind's direction. Together they create these complex, layered structures that shift and change as the comet moves, as the solar wind fluctuates, as the comet's activity varies. It's like watching two painters work on the same canvas using completely different styles. One making broad, sweeping curves, the other drawing precise straight lines. And somehow, the result is this masterpiece written across millions of kilometers of empty space. Now let me tell you where these wanderers come from, because the answer is almost unsettling in its scale. Most comets don't live in the solar system as you might picture it, not among the planets, not in the asteroid belt, not in any region you could reasonably point a telescope and expect to see much. They live in two distant reservoirs, the Kuiper belt, which begins beyond Neptune, and the Oort cloud, near which is so far away it redefines what we even mean by the solar system. The Kuiper belt is the closer of the two, though closer is relative when you're already talking about a region beyond the eighth planet. It's a disk of icy bodies orbiting the Sun, home to billions of comet nuclei just waiting, frozen and dormant in the darkness. Some occasionally get nudged by gravitational interactions, maybe Neptune's pull, maybe a passing body, and begin the long fall inward toward the Sun, where they'll grow their magnificent tails and briefly become visible before retreating back into the outer darkness. But the Oort cloud is something else entirely. It's a spherical shell of comets surrounding the entire solar system, extending nearly halfway to the nearest star. Let that settle for a moment. Halfway to Alpha Centauri. We're talking about a region so vast that light from the Sun takes over a year to reach its inner edge, and possibly 2 years to reach its outer boundary. The Oort cloud isn't just the edge of our solar system, it's the edge of the Sun's gravitational domain, the last place where our star can still claim objects as its own before they drift into interstellar space. Perhaps 1 trillion comets are out there, some scientists estimate, floating in the darkness, too distant and too dark to see, moving in slow ancient orbits that take millions of years to complete. They're the remnants of the solar system's formation, objects that were flung outward during the chaotic early days when giant planets were migrating and everything was finding its place. And they've been there ever since, frozen in time, preserved in the deep cold of space, waiting in a cosmic reservoir that extends farther than our minds can comfortably imagine. Every so often, something disturbs one of them. Maybe a passing star, maybe the gravitational tug of the galaxy itself, and it begins to fall inward on a journey that might take thousands or millions of years, until finally it enters the realm of the planets and we see it blazing across our sky, a visitor from the edge of everything, announcing that the solar system is far, far larger than the comfortable region where the planets orbit. Halley's Comet has been watching human history unfold for over 2,000 years, appearing in our skies like clockwork every 75 to 76 years, and we've been writing about it nearly that entire time. Ancient Chinese astronomers documented it as early as 240 BCE, so carefully recording this strange visitor in their meticulous celestial logs. They didn't know it was the same object returning, of course. They just knew that sometimes a peculiar star with a tail would appear, hang in the sky for weeks and then fade away. But perhaps the most famous historical appearance is the one from 1066 CE, right before the Battle of Hastings. The comet appeared that spring blazing across European skies, and people interpreted it as an omen, though which side it favoured was apparently up for debate. The Normans thought it meant victory for William the Conqueror. The Anglo-Saxons presumably had their own interpretations, and there it is, immortalised in the Bayeux Tapestry, this 230-foot-long embroidered chronicle of the Norman conquest, with people pointing up at the comet in wonder or fear, and this celestial visitor woven into the fabric depicting one of history's turning points. Think about that for a moment. The same object that appeared over the Battle of Hastings also appeared during the American Revolution, during both World Wars, during the fall of the Berlin Wall. Mark Twain was born during its 1835 appearance and died during its 1910 return, which he'd predicted, saying he came in with the comet and expected to go out with it. And he was right. Every human who's ever lived a full life has had the opportunity to see Halley's Comet at most once, maybe twice if they're particularly fortunate. It connects generations across vast spans of time. Someone who saw it in 1910 as a child might have told you about it if you're old enough to remember. And if you saw it in 1986, you'll be quite elderly when it returns in 2061, completing another loop around the sun, another chapter in its ongoing relationship with humanity. We've been watching the same cosmic wanderer for millennia, and it's been utterly indifferent to all of it, to our wars, our empires, our technological revolutions. It just follows its orbit, appearing on schedule, a frozen remnant of the solar system's birth that happens to pass through our neighbourhood every human lifetime or so, connecting us to everyone who ever looked up and wondered what that strange star with the tail might mean. Here's something that feels almost violent when you really think about it. When a comet gets close to the sun, it can lose several tons of material every single second. Not per hour, not per day, per second. Imagine standing on the surface of a comet nucleus as it approaches the inner solar system, though you'd need a spacesuit and magnetic boots because there's virtually no gravity. You'd watch as the sun grows brighter and warmer, and then the ice beneath your feet would start to wake up. Because that's what's happening. The ice has been frozen solid for billions of years, dormant and unchanged since before Earth existed, and now suddenly it's being heated by solar radiation. The ice doesn't melt. There's no atmosphere, no pressure to allow liquid water. It sublimes, going directly from solid to gas, like dry ice evaporating in reverse fast forward. And as it does, it carries dust and debris with it, erupting from the surface in jets and geysers of vapour, several tons per second. That's like losing a small car's worth of material every few seconds. Over the weeks or months that a comet spends near the sun, it can lose millions of tons of mass, material that took 4.5 billion years to accumulate, now streaming away into space to form those magnificent tails we admire from Earth. The comet is being eroded by sunlight itself, slowly evaporating like ice cream melting on a summer day, except this ice cream is kilometres wide and travelling at tens of thousands of kilometres per hour. This means every comet is on a self-destruct timer. Each passage through the inner solar system strips away more of its substance. Some comets are fresh, making their first journey inward from the Oort cloud, rich with volatile materials that explode into spectacular displays. Others are old, worn down by dozens or hundreds of previous approaches, growing fainter with each return until eventually there's nothing left to vaporize. It's a slow dissolution, a gradual transformation from icy nucleus to dust and gas scattered along an orbital path. And all of it happening because the sun's warmth, that same warmth that makes life possible on Earth, is slowly, steadily, inevitably destroying these ancient objects 1 ton at a time, every second they dare to draw close to its light. Now here's something that contradicts everything your eyes tell you when you see a comet shining in the night sky. Comet nuclei are among the darkest objects in the entire solar system. They reflect only about 3 to 5% of the light that hits them. To put that in perspective, they're darker than coal, darker than asphalt, darker than almost anything you encounter in your daily life. If you could hold a piece of comet nucleus in your hand, which, again, please don't try, it would look almost black, absorbent, hungry for light. This seems wrong, doesn't it? Comets are supposed to be made of ice, and ice is bright, reflective, white. Fresh snow reflects about 80 to 90% of sunlight. A snowball practically glows in winter sunshine. So how can something made primarily of ice be darker than charcoal? The answer is a layer of organic compounds, ancient carbon-based molecules that formed in the early solar system, coating the surface like a dark crust. As the comet gets close to the sun and the surface ice vaporizes, it leaves behind this non-volatile material, these dark organics that don't sublimate, creating a crust that just gets thicker with each solar approach. It's like a shell of primordial carbon chemistry, baked onto the surface by repeated exposure to solar radiation. So when we call comets dirty snowballs, the dirty part is doing a lot of work. That dirt is actually complex organic material, possibly including amino acids and other prebiotic compounds. The darkness you'd see if you stood on a comet isn't the darkness of emptiness or purity, it's the darkness of carbon, of organic chemistry, of molecules that might have seeded Earth with the building blocks of life. It creates this strange paradox. Comets appear bright in our sky, with their glowing comas and sweeping tails, but the actual nucleus, this source of all that brilliance, is a dark, coal-black object absorbing nearly all the light that touches it. For the brightness we see isn't reflection, it's emission, transformation. The comet is converting solar energy into vaporization, and that vapor catches the light, glows, creates the spectacle. But the heart of it, the ancient core, remains dark as midnight, darker than almost anything else orbiting the sun, quietly accumulating a crust of organic darkness that's been building for billions of years. There's a theory that's both humbling and slightly unsettling when you let it fully settle in. Scientists believe comets may have delivered much of Earth's water during the planet's early history. The oceans you see today, the water you drink, the rain that falls, the tears that form in your eyes, all of it might have fallen from the sky as frozen chunks over millions of years during an era called the Late Heavy Bombardment. Picture early Earth. Around 4 billion years ago, the planet was hot, volcanic, hostile. Any water that existed on the surface was likely boiled away by the intense heat of formation and the constant bombardment from space debris. And then, over the following hundreds of millions of years, comets and water-rich asteroids rained down on the young planet. Not gently. These were impacts, collisions, violent deliveries travelling at cosmic speeds. But with each strike, they brought water, ice that would vaporize on impact, steam that would condense in the atmosphere, rain that would eventually pool in the lowlands, creating puddles that became lakes, that became seas, that became oceans. Think about that. The Pacific Ocean, all of it, every drop might have arrived via cosmic delivery service, brought by countless comets diving into Earth's gravity well over millions of years. The water cycle that sustains all life on this planet, that shapes weather and climate and makes Earth the blue marble we see from space, might have its origins in the Oort cloud, in those distant reservoirs where frozen water has waited since the solar system's birth. Now, the story is more complicated than that. Recent measurements suggest that many comets have water with a different isotopic signature than Earth's oceans, more deuterium, heavy hydrogen, which means they probably weren't the only source. Water-rich asteroids likely contributed significantly too. But comets were almost certainly part of the delivery system, part of the long, violent process that transformed Earth from a dry, hellish rock into a water world capable of supporting life. So when you look at the ocean, when you feel rain on your face, when you fill a glass from the tap, you might be touching water that once hung frozen in the darkness beyond Neptune, that travelled for millions or billions of years before crashing into a young Earth, bringing the very substance that would eventually make consciousness possible. We are, in a very literal sense, made of comet water, our bodies carrying molecules that fell from space when the world was young, when the solar system was still sorting itself out, when the story of life on Earth was just beginning to be written in cosmic ice. A comet's coma, that fuzzy, glowing cloud surrounding the nucleus, can grow larger than Jupiter, larger than Jupiter. Let that sink in for a moment because the scale is almost impossible to grasp. Jupiter is enormous, a gas giant so massive you could fit more than 1,300 Earths inside it. And yet, the cloud of gas and dust surrounding a comet nucleus only a few kilometers across can expand to become even larger than that planetary behemoth. But here's the thing that makes this even stranger. This enormous cloud is so diffuse, so incredibly thin, that you could fly a spacecraft through it and barely notice you'd entered anything at all. The density is so low that it's essentially a vacuum by Earth standards, just slightly less empty than the already empty space around it. If you were somehow standing inside a comet's coma, you wouldn't see fog or haze. You'd see, basically, nothing. Maybe a very slight glow if you were looking at the right wavelength, but mostly just the stars and the darkness, same as anywhere else in space. It's one of those beautiful contradictions that space seems to specialize in. From Earth, through a telescope, a comet's coma looks substantial, like a real object, something with presence and mass, and in a sense it is. There are billions of tons of material spread throughout that volume, but that material is distributed across such a vast space that the actual density approaches nothingness. You could wave your hand through it, and your hand would encounter maybe a handful of molecules, a few dust particles. Think about it this way. If you could somehow gather up all the material in a coma larger than Jupiter and compress it down, you might get a small hill's worth of dust and ice, maybe enough to fill a few swimming pools, that's all. The rest is just emptiness, space between particles, void masquerading as substance because our telescopes see the cumulative glow of billions of widely separated molecules catching sunlight. It's like looking at fog from a distance and thinking it's solid, only to walk through it and realize it's almost entirely air with just the barest hint of water droplets suspended impossibly far apart from each other. The comet creates this illusion of size, of presence, growing a cloud larger than the biggest planet, but the cloud is more absence than presence, more nothing than something, a ghost of material haunting the darkness around a dark, evaporating core. Just when you think you understand comet tails, the dust tail curving gently, the ion tail pointing straight back from the sun, comets throw you another curveball. Sometimes they develop what looks like a third tail, and this one appears to point toward the sun, which seems to violate everything we just established about how comet tails work. Astronomers call it an anti-tail, and the name is perfect because it seems to be doing exactly the opposite of what tails are supposed to do. But here's the beautiful thing, it's an illusion, a perspective trick. The anti-tail isn't actually pointing toward the sun at all. It's made of large dust particles that the comet has left behind in its orbit on previous passes. These particles are heavier than the fine dust that makes up the normal dust tail, so they don't get pushed as far by solar radiation. Instead, they spread out along the comet's orbital path, creating a trail of debris that just hangs there in space waiting. And then, at certain points in the comet's orbit, when the geometry is just right, when Earth happens to be positioned at precisely the correct angle, we look at the comet and see this trail of particles edge on. It's like looking at a sheet of paper from the side. What's actually a flat plane appears as a thin line, and because of our viewing angle, that line appears to extend toward the sun, creating this illusion of a tail pointing the wrong way. It's a reminder that so much of what we see in astronomy is about perspective, about where we happen to be standing in space when we look. The anti-tail isn't defying physics or breaking the rules about solar radiation pressure. It's just a trail of old debris catching sunlight at exactly the right angle to create something that looks impossible from our particular vantage point on Earth. These anti-tails are relatively rare. You need the right kind of comet leaving behind the right kind of debris trail, combined with Earth being in exactly the right position at the right time. When they do appear, they're usually visible for only a few days or weeks before the geometry shifts and the illusion disappears. The debris trail is still there, of course, spreading along the comet's orbit like breadcrumbs marking its path through space. But we can't see it anymore, at least not as that striking anti-tail that seemed to point toward the sun, challenging our understanding before revealing itself to be nothing more than a beautiful trick of perspective and light. In 1811, a comet appeared in Earth's sky and simply refused to leave. The Great Comet of 1811 was visible to the naked eye for 260 days, nearly 9 months of having this celestial visitor overhead, night after night, a constant presence in the darkness. Most comets make brief appearances, a few weeks at most before fading from view. But this one lingered like a guest who'd found the party too interesting to leave, and people noticed. How could they not? For 3/4 of a year, you could walk outside on a clear night, and there it would be. This luminous visitor with its sweeping tail, bright enough to be unmistakable, present enough to become part of daily conversation. In an era before electric lights, before light pollution dimmed the night sky, this comet would have been spectacular, dominating the darkness with a presence that must have felt almost supernatural. It became so culturally significant that the vintage of wine from that year, 1811, was called Comet wine, and people believed it had special properties. There was this idea that the comet had somehow blessed the grapes, that the wine from that harvest would be extraordinary. And perhaps it was, though probably more because 1811 happened to be an exceptional year for European vineyards regardless of any cosmic visitors. But the association stuck. Even today, if you're lucky enough to find a bottle of 1811 vintage from certain regions, it might be labelled or referenced as Comet wine, carrying forward this 2-century-old connection between celestial mechanics and terrestrial agriculture. It's one of those moments where astronomy intersects with human culture in unexpected ways. The comet didn't care about wine or harvests or human superstitions. It was just following its orbit, evaporating in the sun's warmth, doing what comets do. But for 9 months in 1811, it was present enough, visible enough, persistent enough to work its way into human consciousness, to become associated with fortune and quality and cosmic favour. And then, of course, it left. The comet continued its journey back into the outer solar system, fading from view, returning to the darkness where it had spent the previous thousands or millions of years. The wine remained, aging in cellars, carrying the comet's name into the future. A reminder that sometimes the universe puts on a show long enough that we can't help but weave it into our stories, our traditions, our bottles of extraordinarily rare wine that may or may not taste any different because a ball of ice and dust happened to be visible in the sky when the grapes were harvested. Here's something melancholy if you think about it too long. Short-period comets. Those that orbit the sun in less than 200 years gradually fade and eventually die. They're not immortal. Each pass near the sun strips away more material, more ice, more of the volatile compounds that create those spectacular displays. And eventually, after dozens or hundreds or thousands of orbits, there's simply nothing left to vaporize. The process is gradual, almost imperceptible across human timescales, but relentless. A comet might be brilliant on its first approach from the Kuiper belt, rich with pristine ices that explode into activity when warmed by the sun. But on its second pass it's slightly dimmer. The third pass dimmer still. The surface becomes more and more crusted with non-volatile material, the dark organic compounds we talked about earlier, creating a shell that insulates the remaining ice underneath. Eventually, what you're left with is essentially a dark, rocky core, a dead comet, an extinct comet, something that was once spectacular and is now just another dark asteroid drifting through space. Or sometimes not even that. Sometimes the comet simply falls apart, disintegrates into a stream of debris that spreads along its former orbit. And when Earth passes through that debris stream, we see meteor showers, the remains of a comet that no longer exists, burning up in our atmosphere as tiny fragments, creating streaks of light that last for fractions of a second. It's a kind of death, but also a transformation. The comet doesn't just disappear, it becomes something else, either a dark, inert nucleus that might be mistaken for an asteroid, or a river of dust flowing along its old orbital path, occasionally intersecting Earth to create those annual meteor showers we look forward to. The material doesn't vanish, it just stops being a comet, stops performing that particular cosmic dance of ice and sublimation and glowing tails. Some short-period comets are dying right now, in real time, though the process is slow enough that we measure it across decades or centuries rather than days. We watch them fade, orbit by orbit, seeing less activity each time they return, knowing that eventually they'll make a final pass through the inner solar system and then nothing, just silence, just darkness. Just a small dark object following the same elliptical path it always has, but without the spectacular announcement of its presence. A retired comet, its performing days over, settling into a quiet existence as just another piece of cosmic debris, carrying the memory of what it once was in its dark organic crust. Every August, the Perseid meteor shower lights up Earth's night sky with dozens of shooting stars per hour, and people gather in fields and on rooftops to watch. It's become a summer tradition, a celestial fireworks display that requires no electricity, no special effects, just clear skies and patience. But what people are actually watching, what's creating those brief, beautiful streaks of light is Earth ploughing through the ancient dust trail of Comet Swift-Tuttle. Think about what that means. Comet Swift-Tuttle last passed through the inner solar system in 1992. Before that, 1862. Before that, around 1737. Each time it approached the Sun, it shed material, dust, pebbles, grains of ice, fragments of organic matter, and all of that debris spread out along its orbital path. The comet moved on, heading back toward the outer solar system, but the debris remained, creating this river of particles flowing along the same ellipse that Swift-Tuttle follows. And every year in mid-August, Earth's orbit crosses Swift-Tuttle's orbit, and we drive through that debris field. The particles hit our atmosphere at about 60 kilometers per second, roughly 134,000 miles per hour. And the friction is so intense that they vaporize almost instantly, heating the air around them until it glows. What you see as a meteor, as a shooting star, nears actually the atmosphere burning, excited by a grain of comet dust no larger than a sand particle, creating a streak of light that travels across the sky and vanishes in less than a second. You're watching ancient comet material die, material that might be hundreds or thousands of years old, depending on which loop of Swift-Tuttle's orbit it came from. Perhaps that particular grain of dust was released in 1862, when Abraham Lincoln was president, and it's been drifting along this orbital path ever since, waiting for its eventual collision with Earth's atmosphere. Or maybe it came from the 1737 pass, older than the United States itself, or from a pass before that, older than anyone's memory. Every meteor shower has a parent comet, a source. The Leonids come from Comet Tempel-Tuttle, the Orionids from Halley's Comet, the Geminids, interestingly, from what appears to be an asteroid but might be a dead comet nucleus. Each shower is a memorial, in a way, to material shed long ago by these wandering visitors, material that's been orbiting the Sun for decades or centuries, and now makes its final brilliant appearance as a streak of light across a summer sky. So when you watch the Perseids in August, you're seeing time collapsed. Ancient dust released from a comet years or centuries ago, finally meeting its end in Earth's atmosphere, creating light that travels to your eyes, completing a journey that began when Swift-Tuttle passed close to the Sun and shed some infinitesimally small portion of itself into the void. And it happens every year, like clockwork, Earth passing through the same debris trail on schedule, creating the same show, connecting us to a comet that won't return for another century. In July 1994, humanity witnessed something that had never been seen before, a comet breaking apart and crashing into another planet. Comet Shoemaker-Levy 9 had gotten too close to Jupiter on a previous orbit and been torn into more than 20 separate fragments by the giant planet's immense gravitational forces. And then, over the course of a week, one by one, those fragments slammed into Jupiter's atmosphere at over 60 kilometers per second. Astronomers around the world pointed every telescope they had at Jupiter, watching in real time as these impacts occurred, each fragment hit with the force of millions of nuclear weapons, creating fireballs that rose thousands of kilometers above Jupiter's cloud tops. The impacts left dark scars in the planet's atmosphere, bruises, almost, that were larger than Earth, larger than the entire planet you're standing on right now. These were wounds on Jupiter's face, visible from Earth through amateur telescopes, dark marks that persisted for months before Jupiter's turbulent atmosphere gradually erased them. It was thrilling and sobering in equal measure. Thrilling because we were watching cosmic violence on a scale that's almost impossible to comprehend, seeing direct evidence of how violent the solar system can be. But sobering because it raised an obvious question. What if that had been Earth instead of Jupiter? What if a fractured comet had decided to visit our planet instead? The largest fragments of Shoemaker-Levy 9 were estimated to be about 2 kilometers across. Not huge by comet standards, but large enough, and there were more than 20 of them, though creating a week-long bombardment. If Earth had been the target, each impact would have been catastrophic, extinction level, civilization ending, the kind of event that shows up in the geological record as a boundary between eras. The fact that it happened to Jupiter instead was simply a matter of orbital mechanics and timing. Jupiter in this sense acts as a kind of shield for the inner solar system. Its enormous gravity attracts comets and asteroids, capturing some, deflecting others, occasionally taking direct hits like this that might otherwise have threatened Earth. The planet is so massive that it warps the trajectories of objects passing through the outer solar system, changing the odds, altering paths. Some scientists call Jupiter a cosmic vacuum cleaner, though that metaphor doesn't quite capture the violence of what we watched in 1994. The scars eventually faded. Jupiter's atmosphere is dynamic, constantly churning, and within months the dark marks have been dispersed and mixed into the planet's bands of clouds. But the event remains in our collective memory as a reminder. The solar system is not a calm, peaceful place. Objects collide, comets break apart, planets get hit. And we're fortunate, cosmically fortunate, that Jupiter is out there, massive and gravity-rich, taking some of the impacts that might otherwise head our way, bearing the scars in its atmosphere until they fade again and again, century after century. Comet nuclei rotate as they travel through space, but they don't spin with the smooth, predictable rotation you might expect from a planet or a well-balanced asteroid. Instead, many of them tumble chaotically, wobbling and flipping in irregular patterns that make them difficult to predict. It's not a graceful pirouette through the cosmos. It's more like watching a lumpy potato being tossed end over end, except the potato is several kilometers wide and covered in jets of gas that are actively changing how it spins. Those jets are the key to understanding this chaotic rotation. As the sun heats different parts of the comet's surface, ice sublimates unevenly. Maybe there's a particularly ice-rich patch that faces the sun and suddenly erupts into activity, or maybe the comet's irregular shape causes some areas to heat faster than others. Each jet of gas acts like a tiny rocket engine, pushing against the nucleus, creating torque, changing the rotation. Imagine trying to spin a basketball on your finger, except someone keeps blowing air at it from different directions at random intervals. The ball would wobble, tilt, maybe start spinning around a different axis entirely. That's essentially what's happening to comet nuclei, except the someone is the sun, and the air is jets of sublimating ice, powerful enough to alter the rotation of an object massing billions of tons. This makes studying comets incredibly difficult. When a spacecraft approaches a comet, mission planners can't always predict exactly which face of the nucleus will be pointing which direction at any given time. The rotation period might be changing, the axis might be precessing, that slow wobble like a spinning top that's starting to lose momentum. The whole object might be in a state of tumbling that won't stabilize for years or decades. And here's something even stranger. Some comets rotate so slowly that their day lasts weeks or months, while others spin rapidly, completing a rotation in just hours. The rotation rate depends on the comet's history, how many times it's passed the Sun, how much material it's lost, how those jets have been firing. Older comets that have made many trips through the inner solar system often spin faster because the jet activity has been spinning them up over time, like a figure skater pulling in their arms to rotate more quickly. So as these ancient objects drift through space, they're not moving with any kind of dignity or stability. They're tumbling, wobbling, pushed around by their own evaporation, their rotation constantly being altered by forces they can't control. It's messy and chaotic and utterly unlike the smooth, regular orbits and rotations we see from the planets. Comets, even in their motion, even in how they spin, refuse to be predictable, refuse to follow the clean patterns we'd prefer they maintain. The Rosetta spacecraft spent 2 years orbiting Comet 67P, getting closer to a comet than any mission had before, and among its many discoveries was this unfortunate fact: comets smell absolutely terrible. The scientists analysing the data from Rosetta's instruments described the scent as a combination of rotten eggs, horse urine, formaldehyde, and bitter almonds. Which is to say, if you could somehow stand on a comet and take a deep breath, please don't. You would immediately regret every decision that led to that moment. And the smell comes from the various compounds wafting off the nucleus as it warms and sublimates. Hydrogen sulfide creates that rotten egg odour. It's the same compound that makes volcanic areas and hot springs smell so unpleasant. Ammonia provides the sharp, acrid notes reminiscent of animal waste. Formaldehyde, yes, the same chemical used to preserve biological specimens, adds its own distinctive contribution. And hydrogen cyanide, which has that characteristic bitter almond scent, rounds out this olfactory nightmare. It's almost comical when you think about it. These objects that appear so beautiful from Earth, with their sweeping tails and ethereal glow that have inspired poetry and art for thousands of years, that ancient peoples saw as divine messengers, they reek. They are, chemically speaking, absolutely foul. If you could transport someone from the past forward in time, someone who'd written sonnets about comets, and let them smell what a comet actually smells like, they might reconsider their artistic choices. But there's something oddly fitting about it too. Because comets aren't here to be beautiful for us. They're not cosmic decorations. They're repositories of primitive chemistry, collections of the compounds that existed in the early solar system before life, before planets fully formed, before anything organised itself into the more refined chemistry we're familiar with. That terrible smell is the smell of primordial matter, of molecules that formed in the disk of gas and dust around the young sun. Those same compounds that smell so awful, ammonia, hydrogen cyanide, or formaldehyde, are actually building blocks for more complex organic chemistry. They're ingredients that, under the right conditions, can combine to form amino acids, sugars, the precursors to nucleotides. Life, in a sense, is built from things that smell terrible in their raw form. The stench of a comet is the stench of potential, of chemistry waiting to happen, of molecules that haven't yet been refined into anything as organised as biology. So, Rosetta's discovery, while perhaps disappointing to anyone who'd romanticised comets, was actually revealing something profound. These beautiful objects trailing across our sky are beautiful only from a distance. Up close, they're dark, smelly, irregularly shaped chunks of ancient ice and organics, tumbling through space, reeking of sulfur and ammonia, completely indifferent to our aesthetic preferences, just being what they've always been since the solar system's dawn. Some comets have orbits so long they take millions of years to complete a single trip around the Sun. Millions. These are the long-period comets from the Oort cloud, visitors from such immense distances that their orbital periods stretch beyond human comprehension, beyond recorded history, beyond the existence of our species. Imagine a comet that last passed through the inner solar system 2 million years ago. Homo habilis was just beginning to use stone tools. Human ancestors were barely recognizable as human. Language didn't exist. Agriculture wouldn't be invented for another 1.99 million years. That comet swung around the Sun, grew its tail, shone briefly in the sky above a planet inhabited by primitive hominids, and then headed back out into the darkness. And now it's returning. It's been falling inward for 2 million years, slowly accelerating under the Sun's distant pull, and finally it's close enough for us to see it. This visitor from an era so ancient that nothing about Earth, not the climate, not the species, not the continent's positions, remains the same. The comet is unchanged, though. Frozen in time, preserved in the deep cold of the Oort cloud, it's essentially the same object that appeared 2 million years ago, making its next scheduled appearance. But here's the haunting part. This might be its last visit. As it swings through the inner solar system, the gravitational influence of the planets might alter its orbit just enough that it gets ejected entirely, flung out of the solar system to drift through interstellar space forever. Or maybe its new orbit will bring it back in 100,000 years, or 10,000, or maybe never. The solar system is dynamic, chaotic over long time scales. Comets get their orbits changed, perturbed by planetary encounters, sometimes dramatically. So when we see one of these long-period comets, we're seeing something that might never return, something on a trajectory so vast that its previous appearance predates everything we'd recognize as civilization. It passes through once, maybe once in all of human existence, and then it's gone, heading back out into that immense darkness, following an ellipse so large it takes light years to traverse. These comets pass through the inner solar system only once per age of the world, if that. They're temporal visitors as much as spatial ones, objects whose timescales are so vast that they make our own lives, our own civilization, seem like flickers. We happen to be alive during the brief moment, measured in weeks or months, when this particular comet is visible. Before our time, it was somewhere in the outer darkness. After our time, it will return to that darkness, and we, being human, being temporary, get only this one glimpse before it disappears for longer than human civilization has existed. Here's what makes comets so valuable to science. They contain some of the oldest, most pristine material in the entire solar system. When the Sun was forming 4.6 billion years ago, it was surrounded by a disk of gas and dust, the raw material from which everything would eventually form. The planets grew from collisions and accretion within that disk, heating up in the process, melting, started differentiating, transforming that primitive material into something new through heat and pressure and geological activity. But comets formed far out in the disk, in the cold outer regions where temperatures were low enough for water and other volatiles to freeze, and then they were scattered even farther outward into the Kuiper Belt and Oort cloud, where they've remained ever since in a deep freeze that preserves them almost perfectly. They haven't been cooked by proximity to the Sun. They haven't been geologically processed like planets. They haven't undergone the heating and differentiation that transforms primitive material into rocks and metals. They're time capsules. Studying a comet is like opening a freezer that's been sealed for 4.6 billion years and examining what's inside. The ice, the dust, and the organic compounds, all of it dates back to the solar system's formation, unchanged by the processes that have reshaped everything else. When scientists analyze material from a comet, they're analyzing the original ingredients, the raw components that went into making the sun and planets. This is why comet missions are so important, why scientists get excited about opportunities to study these objects up close or bring samples back to Earth. A comet isn't just a ball of ice and dust. It's a record, a witness to the solar system's birth. The ratios of different isotopes in its water tell us about the conditions in the early solar nebula. The organic compounds reveal what chemistry was happening in the disk before planets formed. Voster dust grains preserve information about the interstellar material that collapsed to form the sun in the first place. Before Earth existed, before the Moon, before Mars had water, and Venus was wrapped in acid clouds, the material in these comets was already frozen, already drifting, already carrying the record of what came before, and it's been waiting out there ever since, preserved in conditions so cold and so stable that molecular structures from the solar system's infancy remain intact, ready to be studied by beings made of rearranged stardust who are curious about their own origins. We are, in a sense, studying our own history when we study comets. We're looking at the raw materials that went into making Earth, examining the chemistry that existed before anything we'd call geology or biology or climate. It's the most direct connection we have to the solar system's beginning, frozen in chunks of ice orbiting in the darkness, occasionally falling inward where we can catch them and read the ancient messages written in their chemistry. The nucleus of a comet, that solid core beneath all the gas and dust, is extremely porous, with a density less than cork. If you could somehow grab a cubic meter of comet material and weigh it, it would be lighter than the same volume of many common materials you encounter every day. It's more like frozen foam than solid ice, full of empty spaces, gaps, voids that make up a significant fraction of its volume. This was a surprise when scientists first measured it accurately. You'd expect ice to be dense, solid, heavy. A block of water ice has a density close to 1 gram per cubic centimetre. It barely floats in water, but comet material comes in at around 0.4 to 0.6 grams per cubic centimetre, sometimes even less. It's almost half-empty space, like cosmic Swiss cheese or a frozen sponge, and this is the comparison that helps it make sense, like snowflakes that have gently accumulated over billions of years without ever being compressed into solid ice. Because that's essentially how comet nuclei formed. They didn't condense as single solid objects. They accreted gradually in the outer solar system, with particles of ice and dust gently sticking together through low-velocity collisions. There was no gravity strong enough to compress everything into a solid mass, no heat to melt the ice and let it refreeze into a denser structure. In just gentle accumulation, particle by particle, building up these fluffy, fragile structures that held together through molecular forces and the tiniest whisper of self-gravity. If you could hold a piece of comet nucleus in your hand, and again, setting aside the impossibility and danger of this, it would be crumbly, fragile, almost delicate. You could probably break it apart with your fingers like compressed snow or dried cork. It wouldn't feel like a rock. It would feel insubstantial, lighter than you expected, porous enough that if you squeezed it you might compress it noticeably. This porosity is actually important for understanding how comets behave. Those jets we talked about earlier, those gas eruptions, they're able to happen because the nucleus is permeable. Heat from the sun can penetrate into the interior, sublimating ice below the surface, and the gas can work its way through the porous structure to escape. If comets were solid, dense objects, they'd behave very differently. The porous structure allows them to outgas efficiently, to lose material from beneath their surface crust, to develop the activity that makes them spectacular. So these ancient objects, these remnants from the solar system's formation, are not just old, they're also fragile, delicate, held together by forces barely stronger than the vacuum around them, porous enough that they're more emptiness than substance, time capsules made of foam and shadow, carrying frozen memories from an era before planets, drifting through space in structures so fragile they seem like they shouldn't exist at all, and yet they've persisted for billions of years, waiting in the cold dark, as ready to fall sunward and reveal themselves to anyone patient enough to watch. In 2014, scientists studying Comet 67P made a discovery that still feels slightly impossible. The comet was releasing molecular oxygen, O2, the same oxygen we breathe, that had been trapped in its ice since the solar system formed. Not oxygen created by some chemical reaction happening now, not oxygen that had somehow contaminated the comet recently, but primordial oxygen, oxygen atoms that bonded together over 4.6 billion years ago and have remained paired ever since, frozen in ice, waiting. This was unexpected because molecular oxygen is reactive. It tends to bond with other elements, carbon, hydrogen, nitrogen, forming more stable compounds. The fact that O2 existed in the early solar nebula and then stayed as O2, preserved unchanged for billions of years, challenges some assumptions about the chemistry of the early solar system. It suggests the ice in comets formed very quickly, freezing this oxygen in place before it had time to react with anything else. Think about what that means. Every molecule of O2 coming off Comet 67P is older than Earth, older than the Sun's fusion reactions igniting, older than planets, older than moons, older than everything except the material that collapsed to form the solar system in the first place. These oxygen molecules existed when the solar system was just a disk of gas and dust around a newborn star, and they've been locked in ice ever since, unchanged, unreacted, preserved in a frozen state for longer than geology has existed. When the Rosetta spacecraft detected this oxygen, it was measuring something from the very beginning, mere from before the story really started, and now as the comet approaches the sun and warms, this ancient oxygen is being released, sublimating into space, finally free after 4.6 billion years of frozen storage. The molecules drift away from the nucleus, carried by the solar wind dispersing into the vastness of space, their brief moment of detection by a human spacecraft being the only recognition they'll ever receive for their extraordinary age. It's one of those discoveries that makes you pause. We tend to think of the early solar system as a violent, chaotic place, which it was, but here's evidence of molecular structures forming in that chaos and then being preserved, perfectly intact, for billions of years. The comet has carried this oxygen through the entire history of the solar system, through the formation of Earth, through the rise of life, through the evolution of organisms that would eventually breathe oxygen created by photosynthesis. And all the while, locked in ice, there was this other oxygen, older oxygen from before any of that, waiting to be released when the comet next approached the Sun. Some comets aren't singular objects at all. They're contact binaries, two or more separate nuclei travelling together, sometimes actually touching, sometimes orbiting each other at such close distances they appear as one object. Comet 67P, which the Rosetta mission studied extensively, turned out to be one of these, a strange duck-shaped object that's actually two lobes connected by a narrow neck, like someone stuck two misshapen potatoes together and sent them spinning through space. Scientists aren't entirely sure how these contact binaries form, and maybe two separate comets had a very gentle collision, and when you're in the low-gravity environment of the outer solar system, collisions can be gentle, more like a soft bump than a catastrophic impact. The two objects touched, and mutual gravity, weak as it was, held them together. Or maybe a single comet underwent enough stress, perhaps from rapid rotation or uneven sublimation, that it split into two pieces, and those pieces stayed close, eventually settling into contact with each other. What makes this fascinating is that you can often see the boundary where the two objects meet. With 67P, the neck region was clearly distinct, a narrow connection between two larger lobes, and the two sides had different properties, slightly different compositions, different activity levels, different surface features. They were individuals that had become a pair, or perhaps siblings that had split and then reunited, each maintaining some of its distinct character, even while being part of a larger whole. This creates some interesting behaviours. The gravitational field around a contact binary isn't uniform, it's lumpy. Stronger near the two main masses, weaker in the connection region. If you were standing in the neck area of 67P, you'd be pulled toward both lobes simultaneously, creating a strange sensation of being gently tugged in two directions at once, though the forces would be so weak you'd barely notice. And if you jumped, you might not come back down. The escape velocity in some regions of the comet is less than walking speed. The fact that these structures can exist at all is a testament to how gentle the environment of deep space can be. On Earth, geological processes would tear such formations apart or compress them into single, more stable shapes. But out in the Kuiper Belt, or in the Oort cloud, an object like this can persist for billions of years without disturbance. Two pieces barely held together by the weakest whisper of gravity, touching at a single point, rotating together through the darkness, waiting for the rare occasion when they'll pass close enough to the Sun to warm up and become active. When these contact binaries do become active, the neck region often shows unusual behaviour. Jets preferentially emerge from certain areas, the two lobes heat at different rates, and the whole structure can undergo complex rotational changes as mass is lost unevenly. It's like watching two dancers trying to maintain their balance while both are slowly evaporating, and are creating this delicate, unstable dance of gravity and sublimation and rotation, all playing out across an object that barely exists as a unified whole in the first place. The Stardust mission did something remarkable. It flew through the coma of Comet Wild 2 at over 6 kilometers per second, collected thousands of particles of actual comet dust in an aerogel collector, and then brought those samples back to Earth in 2006. For the first time, scientists could examine comet material in laboratories with instruments far more sophisticated than anything that could fit on a spacecraft. They could take their time, run multiple analyses, really interrogate these tiny grains about their origins and composition. And what they found was simultaneously expected and startling: amino acids. organic compounds. Glycine, the simplest amino acid, was definitely present. Other complex organic molecules were scattered throughout the samples. The building blocks of proteins, the fundamental components of life as we know it, were right there in the comet dust, formed in space, created through chemistry that happened either in the early solar nebula or perhaps even earlier in the interstellar clouds that existed before the Sun formed. This discovery strengthened an idea that had been gaining support for decades. Maybe life's ingredients didn't originate on Earth. Maybe they were delivered here, scattered across the young planet by countless comets and asteroids during those early, violent eons. The chemistry of life might be universal, or at least common, happening naturally wherever conditions allow organic molecules to form and persist. But here's what makes it even more interesting. The amino acids in the comet samples weren't contamination from Earth. Scientists could tell because they had unusual isotopic ratios, markers that showed they formed in space rather than through biological processes. This was genuine extraterrestrial organic chemistry, the same kinds of molecules that living things use, but created through non-biological processes in the cold of space or the warmth of the early solar nebula. Imagine the implications settling in slowly, like dust. The molecules that make you possible, amino acids that combine to form proteins, that fold into enzymes, that catalyze the reactions that constitute life, might have first arrived on Earth as comet dust. Tiny particles, each one microscopic, each one carrying a few molecules of organic compounds, raining down on the young planet by the trillions, accumulating in tidal pools and volcanic vents and shallow seas, waiting for the right conditions to start doing something more interesting than just existing. You might be made of comet dust. Not metaphorically, not poetically, but literally. The carbon atoms in your cells, the nitrogen in your DNA, the organic molecules that allow you to think and breathe and wonder about comets, they might have fallen from space 4 billion years ago, delivered by objects like Wild 2, surviving impacts and heat and radiation, to eventually become part of something that could look back up at the sky and recognize its own origins. The stardust samples sit in laboratories now, tiny grains pressed into aerogel still being studied years after their return. Each grain carries information about the early solar system, about organic chemistry in space, about the pathways that led from simple molecules to complex ones to, eventually, to life. They're evidence that the universe is full of the chemistry that makes biology possible, that the ingredients for life aren't special or rare but are scattered throughout space, waiting in frozen comets, drifting in interstellar clouds, perhaps falling on planets around other stars even now. Some comets get so close to the sun they're called sun grazers, and their fate is often to evaporate completely within hours of their closest approach. These are comets with perihelia, the closest points in their orbits, that bring them within a few 100,000 kilometers of the sun's visible surface, sometimes even closer. At those distances, the temperatures are unimaginable, thousands of degrees, and a comet that spent billions of years frozen in the outer solar system suddenly finds itself in an environment so hostile it simply can't survive. The SOHO spacecraft, which watches the sun continuously from a stable orbit, has discovered over 4,000 of these doomed comets since the 1990s. Most of them were previously unknown, small objects on their first and last approach to the sun, visible only because SOHO's instruments can detect faint objects near the solar disk. and then, one by one, they disappear. Some break apart before reaching perihelion, shattered by tidal forces or destroyed by the intense heating. Others make it all the way to their closest approach and then simply end. They evaporate entirely, their material dispersed into the solar wind. Nothing left but a faint stream of vapor that quickly dissipates. It happens fast. A comet might be visible for a day or two as it approaches, growing brighter, developing a tail, showing signs of activity. And then it swings behind the sun from our perspective, and when it should emerge on the other side, nothing. It's gone. Completely evaporated, transformed from a solid object into scattered atoms in the span of hours. If it was a large comet, maybe some fragments survive. But often, especially with smaller sun grazers, there's no remnant at all. The comet existed, and then it didn't. There's something almost sacrificial about it. These objects have travelled for thousands or millions of years, falling inward from the outer solar system, accelerating under the sun's gravity, heading toward a destination that will destroy them. And they don't have consciousness, of course. They can't know what's coming. But if they could, would they turn away? Would they alter course? Or would they accept that this is what they were always meant to do? Fall toward the sun until there's nothing left but light and vapor? Many sun grazers belong to families, groups of comets with similar orbits, suggesting they're fragments from larger comets that broke apart on previous passes. The Comets family is the largest, containing hundreds or thousands of comets that all trace back to a single massive comet that broke up centuries or millennia ago. So in a sense, we're watching the final chapters of a longer story, fragments of something that used to be whole, each piece making its last dive toward the sun, completing a trajectory that began when the parent comet shattered. And the sun, indifferent as always, accepts these visitors and destroys them with the same radiation that makes life possible on Earth. It's not cruelty, it's just physics, just the inevitable consequence of a small, frozen object venturing too close to a stellar furnace. But watching it happen, seeing comet after comet disappear into the sun's glare and never emerge, creates this sense of witnessing something both beautiful and tragic, these ancient objects choosing, or being forced, to make the ultimate sacrifice, giving themselves entirely to the light. For most of human history, comets were seen as omens, harbingers of disaster, war, famine, plague, or the death of kings. Ancient civilizations watched these unpredictable visitors appear in the sky and assumed they meant something, that the universe was sending a message, usually a warning. Chinese astronomers kept meticulous records of comet sightings, not just for scientific curiosity, but because the emperor needed to know when heaven was displeased. Roman historians noted comets appearing before political upheavals and military defeats, connecting celestial events with earthly catastrophes. Even Shakespeare referenced this belief. In Julius Caesar he wrote, "When beggars die, there are no comets seen. The heavens themselves blaze forth the death of princes." The idea being that the cosmos itself reacted to the death of important people, announcing it with spectacular celestial displays. It's almost touching in its anthropocentrism, the belief that human affairs were so significant that the heavens would go out of their way to comment on them. Of course, we know now that comets don't care about human politics or mortality, or they're following orbital mechanics, not prophetic schedules. When a comet appeared before a disaster, it was pure coincidence, but because disasters of one kind or another are always happening somewhere, it was easy to find correlations. A comet appears, and within the next few months somewhere in the world, there's a battle or a plague or a political assassination, and the connection gets recorded, remembered, passed down as evidence that comets are omens. But there's something worth preserving in that old belief, even as we understand it was wrong, because in a way, comets are messages, just not the kind ancient peoples thought. They're messages from the past, from the solar system's formation, carrying information about where we came from and what the early conditions were like. They're omens in the sense that they warn us the solar system is dynamic, violent, capable of sending large objects on collision courses with planets, including ours. The fear that comets inspired wasn't entirely misplaced, just misinterpreted. When people saw comets and felt dread, they were responding to something real, the visceral understanding that these objects don't belong to our tidy, predictable sky of fixed stars and wandering planets. They intrude from elsewhere, from the outer darkness, following paths we can't predict without careful calculation. That sense of unpredictability, of something entering our space from beyond our understanding, was legitimate. They just attributed the wrong kind of meaning to it. Now we know what comets actually are, and in some ways that knowledge is more unsettling than the old superstitions. Because instead of being messages from gods or fate, they're just chunks of ice and dust following physics, and some of them are on trajectories that could intersect Earth, and there's no cosmic meaning to whether they hit us or miss. The universe isn't sending warnings, it's just operating according to gravitational equations, indifferent to whether those equations result in spectacular light shows or extinction events. Maybe the ancients had it easier, thinking comets were omens. At least an omen implies someone's paying attention, implies there's meaning behind the pattern. The modern understanding that comets are random, that their appearances mean nothing except that orbital mechanics brought them into view, is in some ways harder to accept. We've traded the fear of divine displeasure for the understanding that we live in a universe that doesn't notice us at all, where comets appear because math says they should, not because anyone wanted to send a message. The longest comet tail ever measured stretched for 570 million kilometers, nearly 4 times the distance from Earth to the Sun. Let that number sit for a moment, because it's genuinely difficult to comprehend. If you could somehow stretch that tail out in a straight line, it would reach from the Sun almost to Jupiter. This record belongs to the Great Comet of 1843, which put on such a spectacular display that people around the world stopped their daily lives to watch it cross the sky. Imagine standing on Earth and looking up at something so vast that light itself takes over half an hour to travel from one end to the other. The tail wasn't solid, of course. It was made of incredibly diffuse gas and dust, so thin that you could see stars through it, but still the sheer scale of it defies easy understanding. A structure created by an object perhaps 10 kilometers across, extending across a distance that would take light 31 minutes to traverse. And here's what makes it even more remarkable. That tail was visible from Earth. People with the naked eye could see this enormous streamer stretched across the sky, sweeping through constellations, dominating the night. In an era before electric lights, before light pollution, when the night sky was still truly dark, this comet would have been an overwhelming presence. Not just a point of light or a small smudge, but an actual structure spanning a significant portion of the visible sky. The tail formed through the same process we've discussed, solar wind and radiation pressure pushing material away from the nucleus. But the Great Comet of 1843 was particularly active shedding enormous amounts of material, and its trajectory brought it close enough to the Sun that the solar wind was especially strong. The combination created this extraordinary display, this tail that just kept extending, streaming behind the comet like a banner unfurled across the solar system. People who saw it wrote about it in terms that sound almost mystical. They described it as looking like a sword hanging in the sky, or a river of light flowing through the stars. Some thought it was terrifying, others found it beautiful, and most probably felt both things simultaneously. That mix of awe and unease that comes from witnessing something that reminds you how small you are, how vast the cosmos is, how little control we have over anything beyond our immediate surroundings. The comet itself has long since moved on, continuing its orbit, perhaps heading back toward the outer solar system, or maybe ejected entirely. The tail dispersed, its material now scattered along the comet's orbital path or blown outward by the solar wind. But for a few weeks in 1843, there was a structure in the solar system larger than the orbit of Mars, created by a tiny nucleus losing mass to the Sun's radiation, growing a tail so long it could have connected the inner planets, stretching across distances that make planetary orbits seem modest by comparison. We probably won't see its equal again in our lifetimes. Comets that bright, that active, passing that close to the Sun are rare. We get smaller displays, less dramatic tails, but nothing approaching 570 million kilometers of glowing vapor streaming through space. The Great Comet of 1843 remains the record holder, a reminder that sometimes the universe creates spectacles so grand they exceed our ability to find adequate comparisons, monuments of light and vapor that exist briefly and then fade, leaving only descriptions and measurements to prove they were ever there at all. Here's a small mystery that took scientists over a century to fully explain. Some comets develop green heads, glowing green comas that surround the nucleus, but that green colour never extends into the tail. The coma can be brilliantly green, but the tail remains white, yellow, blue, anything but green. And for a long time, no one knew exactly why. The green glow comes from diatomic carbon molecules, C2, two carbon atoms bonded together, that get excited by solar ultraviolet radiation and then emit light in the green part of the spectrum as they relax back to their ground state. But why doesn't that green colour continue into the tail? The carbon molecules are there, carried along with all the other material streaming away from the nucleus. They should continue glowing green as they drift into the tail region, and yet they don't. The boundary is often quite sharp. Green coma, non-green tail, with a visible transition between the two. It wasn't until 2021 that scientists finally confirmed the mechanism. The C2 molecules are fragile. Solar radiation doesn't just excite them, it also breaks them apart, splitting the two-carbon bond and destroying the molecule. And this photodissociation happens relatively quickly, on timescales of about a day or two. So the C2 molecules glow green while they're in the dense coma, close to the nucleus, but by the time they've drifted far enough away to be part of the tail, they've been destroyed by the same solar radiation that was making them glow. The tail contains the fragments, individual carbon atoms and other breakdown products, but not the intact C2 molecules needed for that characteristic green emission. It's one of those solutions that seems obvious in retrospect, but required careful laboratory work and computer modelling to confirm. The green coma is a temporary phenomenon, a brief glow that lasts only as long as the molecules remain intact. which isn't very long once they're exposed to intense solar UV radiation. The comet is creating these molecules continuously as its nucleus outgasses, but it's also destroying them just as continuously, creating this dynamic equilibrium where the green glow exists in a bubble around the nucleus but can't propagate into the tail. So when you see images of green comets, and they can be strikingly, vividly green, like something from science fiction, you're seeing a particular kind of chemistry happening in a particular location. The green tells you that carbon molecules are being liberated from the nucleus, excited by sunlight, emitting their characteristic wavelength, and then being destroyed before they can travel very far. It's a marker of both creation and destruction happening simultaneously, a colour that signals activity and fragility in equal measure. The fact that it took until 2021 to definitively explain this is a good reminder that there are still mysteries in even the most observed phenomena. People had been noting the green comas and non-green tails for over 100 years, hypothesizing about the cause, but it required modern laboratory techniques and computational models to actually pin down the mechanism. Science sometimes moves slowly, but it gets there eventually, explaining the small mysteries one by one, turning observations into understanding, even when the observations are of something as ephemeral and transient as a green glow around a comet's head. Jupiter acts as a kind of cosmic bodyguard for the inner solar system, its enormous gravitational field attracting and capturing many comets before they can reach Earth, Mars, Venus, or Mercury. This isn't intentional, of course. Jupiter doesn't have agency, doesn't make decisions about which comets to intercept. But the math works out such that Jupiter's gravity significantly alters the trajectories of objects passing through the outer solar system, and many that might have eventually wandered inward get captured, deflected, or in some cases directly impacted into Jupiter's atmosphere. The numbers are staggering. Jupiter is so massive, more than twice the mass of all other planets combined, that it creates a gravitational well that dominates the outer solar system. Comets passing anywhere near Jupiter can have their orbits radically changed. Some get flung outward, regaining so much velocity they're ejected from the solar system entirely. Others get their orbits shortened, becoming short-period comets that now orbit the Sun in just a few years, and some, like Shoemaker-Levy 9, get pulled into Jupiter itself, ending their journey in a fiery collision. Without Jupiter, Earth would likely be struck by comets far more frequently than it is. Some estimates suggest the impact rate could be hundreds or even thousands of times higher if Jupiter weren't there, sweeping up or deflecting objects that would otherwise have chaotic orbits through the inner solar system. This has implications for the development of life on Earth. Fewer catastrophic impacts means more stable conditions, more time for evolution to work, less chance of extinction events resetting biological complexity. But it's not a perfect protection system. Jupiter doesn't catch everything. Plenty of comets still make it through to the inner solar system. We see them regularly after all. And sometimes Jupiter's gravity can work against us, perturbing a comet's orbit in a way that sends it inward rather than deflecting it away. The solar system's gravitational dynamics are complex, chaotic over long timescales, and Jupiter's influence can produce unpredictable results. Still, on balance, Jupiter's presence has likely been beneficial for Earth. It's cleaned up the outer solar system significantly, reducing the population of objects that might otherwise be on planet-crossing orbits. The giant planet sits out there at 5 astronomical units, massive and indifferent, its gravity warping the trajectories of anything that passes nearby. occasionally taking direct hits, occasionally ejecting objects into interstellar space, generally acting as a stabilizing force in an otherwise chaotic environment. It's strange to think that our existence might depend partly on the presence of a gas giant we'll never visit, a planet with no solid surface, made mostly of hydrogen and helium, existing primarily to be massive enough to perturb the orbits of icy objects in the outer solar system. But that's how complex systems work. Everything affects everything else, and the conditions that allow for life on one planet might depend on the gravitational influence of another planet millions of kilometers away, protecting without knowing it's protecting. A cosmic accident that happens to work in our favor. Some of the asteroids we observe today aren't really asteroids at all, they're extinct comets. Objects that were once active and spectacular, but have now lost all their volatile materials after countless passages near the Sun. They've transformed from tail-sprouting wanderers into silent rocky husks that drift through space, indistinguishable from any other asteroid except for subtle clues in their orbits and compositions. The transition from active comet to dead asteroid is gradual, almost imperceptible across human timescales. Each orbit brings the comet close to the Sun. Each approach strips away more ice, more volatiles, more of the material that creates activity. The surface develops a thicker and thicker crust of non-volatile material, that dark organic layer we discussed earlier, until eventually it becomes so thick that heat from the Sun can no longer penetrate to the ice underneath. Or maybe there simply isn't any ice left to sublimate, and then, one orbit, the comet arrives near the Sun and nothing happens. No tail forms, no coma develops. The object is still there, still following the same elliptical path it's been following for thousands of years, but now it's just a dark, inert rock. An asteroid, for all practical purposes, even though its history is completely different from asteroids that formed in the asteroid belt and never contained significant ice. Scientists can sometimes identify these extinct comets by their orbits. If an asteroid is on a highly elliptical, comet-like orbit, especially one that brings it close to the Sun, that's suspicious. Or by their composition. Spectroscopic analysis might reveal surface materials more consistent with cometary nuclei than with typical asteroids. But in many cases, it's genuinely difficult to tell whether you're looking at a true asteroid or an extinct comet. They've become functionally identical, even though their origins were different. There's something melancholy about this transformation. These objects were once beautiful, active, capable of growing magnificent tails and capturing human attention. They were performers, spectacles, visitors from the outer darkness that announce themselves with light and vapor. And now there are just rocks, dark, silent, forgotten, drifting through the same orbits but no longer capable of the displays that once defined them. But maybe there's also something peaceful about it. After thousands of orbits, after millions of years of being slowly destroyed by solar radiation, these comets get to rest. They no longer have to endure the violence of sublimation, the loss of mass, the chaotic rotation caused by uneven outgassing. They just drift, inert and stable, their performing days over, settling into a quiet retirement among the asteroids. Some of them might still have ice buried deep in their interiors, beneath thick crusts that protect it from solar heating. If conditions changed, if the orbit shifted, bringing the object closer to the Sun, or if an impact broke through the crust, maybe they could become active again, briefly resurrecting their comet nature before lapsing back into silence. But for most, the transformation is final. What was once a comet is now an asteroid, and all that remains of their former glory is an unusual orbit, and perhaps a few spectroscopic signatures that hint at a more dramatic past. In October 2007, Comet Holmes did something unprecedented. It suddenly brightened by a factor of about 500,000 in just 42 hours, 500,000 times brighter. It went from being invisible to the naked eye, requiring a telescope to see at all, to being easily visible without any optical aid, appearing as a bright, fuzzy star in the constellation Perseus. Astronomers around the world watched in real time as this faint comet exploded into prominence, growing a coma that became larger than the Sun in angular size. No one saw it coming. Holmes was a known periodic comet discovered in 1892 with a reasonably well understood orbit. It passed near the Sun every 6.9 years and typically put on modest displays. Nothing spectacular, just a faint comet doing comet things. And then, on October 24th, 2007, something happened. An outburst so massive and so sudden that it transformed the comet almost overnight. The theories about what caused it range from plausible to speculative. Maybe a large cavity of ice beneath the surface suddenly collapsed, exposing fresh material that rapidly sublimated. Maybe a cliff face on the rotating nucleus became exposed to sunlight and triggered a massive eruption. Maybe there was some kind of explosive chemical reaction in the interior. Certain ices, when mixed, can react exothermically, potentially triggering cascading sublimation. Or perhaps it was an impact, a small meteoroid hitting the nucleus at just the right spot to breach the crust and trigger outgassing. The truth is, we still don't know for certain. The event happened too quickly to prepare detailed observations, and by the time astronomers fully mobilized their instruments, the outburst was already underway. They could measure the brightness, track the expanding coma, analyze the spectrum of the light, but the trigger, the initial cause, remained hidden in those first few hours when the comet was transforming too rapidly to fully observe. What we do know is that the coma expanded to become the largest object in the solar system by volume for a brief period, not the most massive, but the largest. It was bigger than the Sun in terms of the space it occupied, though still incredibly diffuse, still more vacuum than substance. Amateur astronomers could see it easily, could watch it change night by night as the coma continued expanding and evolving. It was one of those rare events that brought astronomy to everyone. Not just those with telescopes, just go outside, look at Perseus, and there it was. And then, gradually it faded. The outburst material dispersed, the coma contracted, and Comet Holmes returned to being a faint object requiring telescopes to observe. It completed its orbit and returned to the outer solar system, leaving behind just measurements and photographs, and a reminder that comets can surprise us, can do things we don't expect, can suddenly become prominent members of the night sky through mechanisms we don't fully understand. It's humbling, really. We have spacecraft orbiting comets, we've landed on them, we've collected samples and analysed their composition in detail, and yet, a comet can still surprise us, can still do something so dramatic and so sudden that we're left piecing together what happened after the fact. These objects, ancient and simple as they are, retain the capacity for unpredictability, for moments of explosive activity that remind us how much we still have to learn about even the smallest and oldest members of our solar system. In 2005, NASA's Deep Impact mission did something that sounds almost aggressive. It deliberately crashed a refrigerator-sized impactor into Comet Temple, one at 37,000 kilometers per hour. This wasn't an accident or a close call. It was intentional, a controlled collision designed to excavate material from beneath the comet's surface crust so scientists could study what was hidden inside. The spacecraft released the impactor, which carried no instruments of its own, just mass and velocity, and then retreated to a safe distance to watch and photograph the collision. The impact occurred on July 4th, 2005, creating a flash of light visible from Earth and excavating a crater estimated to be somewhere between 100 and 200 meters across. But here's what surprised everyone. The crater was far larger and less defined than models had predicted, and the material ejected from the impact was incredibly fine, more like talcum powder than the chunky ice and rock fragments scientists expected. The comet's interior turned out to be far fluffier, far more porous than anyone had anticipated. Instead of hitting something with the consistency of dirty ice or frozen soil, the impactor struck material so fine and so loosely packed that it behaved almost like a powder. The collision threw up enormous clouds of dust that obscured the crater itself, so much dust that the cameras couldn't actually see the crater floor, couldn't measure its exact depth or shape. It was like punching a pillow filled with dust. The impact created a cloud rather than a clear cavity, and the ejected material just kept coming, streaming away from the nucleus for days after the impact. This discovery fundamentally changed how scientists think about comet interiors. They're not solid chunks of ice with some dust mixed in. They're more like cosmic dust bunnies, incredibly fragile aggregations of tiny particles held together by the weakest forces, so loosely packed that when you hit them at 37,000 kilometers per hour, they just puff. The dust goes everywhere, creating clouds, but there's no resistance to speak of, no solidity. Think about what this means for comet formation and structure. These objects accreted gently in the early solar system, particles sticking together through electrostatic forces and the tiniest whisper of gravity, building up over time into larger and larger clumps but never compressing into anything truly solid. They're like snowflakes that have been accumulating for billions of years without ever getting compacted into ice. The interior structure remained pristine, untouched by the processes that would have compressed or altered it. And this fluffiness explains a lot about comet behavior. It explains why they can break apart so easily. There's nothing holding them together except the weakest forces. It explains why jets can form from deep within the nucleus, heat can penetrate through the porous structure, and gas can escape through the interconnected voids. It explains why comets have such low densities. They're mostly empty space between particles. The Deep Impact mission was supposed to be a simple experiment. Hit a comet, see what comes out, analyze the composition. But what came out was mostly dust. So much dust that it obscured the results, creating more questions than answers. The composition was interesting, certainly, but the real revelation was about structure, about texture, about the fundamental nature of these objects being far more delicate and insubstantial than anyone had quite imagined. We learned that you can't think of comets as solid objects in any conventional sense. They're aggregations, accumulations, barely they're collections of particles that happen to be travelling through space together, one held by forces so weak that a spacecraft impact doesn't so much excavate a crater as create a cloud of ancient dust that billows into space like a cosmic dandelion being blown apart. Comets can develop jets, streams of gas and dust that spray from specific locations on the nucleus. And these jets don't just create beautiful displays, they actually act as natural thrusters, capable of changing the comet's trajectory over time. It's one of those effects that seems small in the moment but becomes significant across decades or centuries, making predictions about where a comet will be in the future surprisingly difficult. Here's how it works. As a comet rotates, different areas of the surface are exposed to sunlight at different times. When an ice-rich area rotates into sunlight and begins to heat up, it can start out gassing vigorously, or creating a jet of vapor and dust shooting away from the surface. That jet is mass leaving the comet at high velocity, and by Newton's third law, there's an equal and opposite reaction, a tiny thrust pushing the nucleus in the opposite direction. For a comet nucleus massing billions of tons, these jets produce minuscule accelerations. We're talking about forces measured in fractions of a Newton pushing against objects the size of mountains. But these forces are continuous during active periods, and they're not always balanced. If one hemisphere has more volatile ice than the other, or if the rotation axis is tilted in a particular way, the jets can create a net thrust in a specific direction, slowly altering the comet's orbit. Over years or decades, these tiny changes accumulate. The comet arrives at perihelion a few hours earlier or later than predicted. Its trajectory is slightly different than calculations suggested it should be. For comets that make frequent passes, short-period comets, these non-gravitational forces can become the dominant source of uncertainty in predictions. Scientists have to account for them, estimating the strength and direction of jet activity based on previous observations, essentially trying to predict how the comet will push itself around. This is why comet predictions sometimes fail. In the 1800s, astronomers would calculate when a comet should return based purely on gravitational forces, and then it would show up weeks or months off schedule. Or sometimes not show up at all, having been pushed onto a different trajectory entirely by cumulative jet activity over multiple orbits. Before scientists understood this non-gravitational effect, it was baffling. The math should work. Orbital mechanics is precise, but comets kept defying predictions. Now we know comets are pilots of a sort, steering themselves through space using engines they can't control. The jets fire based on which side is facing the sun, which depends on rotation, which might itself be changing due to the jets. It's a feedback loop, chaotic and unpredictable, creating behavior that looks almost intentional, but is actually just physics playing out in complex ways. Some comets spin up over time, rotating faster and faster as asymmetric jets push against them like a cosmic carousel. Others might slow down if the jets happen to fire in opposition to the rotation. The whole system is dynamic, constantly changing, with each approach to the sun potentially altering the rotation rate, the jet locations, the orbit itself. Comets are not passive objects following fixed paths. They're active participants in their own motion, however unintentionally, changing their futures with every burst of vapor that erupts from their surfaces. The Oort cloud, home to perhaps 1 trillion comets, has never been directly observed. We've never taken a picture of it, never seen it through a telescope, never detected its objects except when they fall inward and become visible in the inner solar system. Everything we know about the Oort cloud is inference, deduction from the behavior of long-period comets that arrive from every possible direction in the sky. Think about that for a moment. One of the largest structures associated with our solar system, and yet extending potentially 2 light-years from the Sun, containing more frozen objects than we can easily count, and we've never actually seen it. It's too far away. The individual objects are too small and too dark. Even our best telescopes looking in the right direction would see nothing but darkness and distant stars. The Oort cloud exists in a realm beyond direct observation, known only through its effects. The reasoning goes like this. Long-period comets arrive from all directions, not just from the ecliptic plane where the planets orbit, but from above and below, from every angle. This implies a spherical distribution of comets surrounding the Sun, not a disk. The orbits have extremely large semi-major axes, suggesting these comets spend most of their time at enormous distances, and occasionally something, maybe a passing star, maybe gravitational perturbations from the galactic tide, nudges one of these distant objects just enough that it begins the long fall inward. So we infer a vast spherical cloud of icy bodies, extending from perhaps 2,000 astronomical units out to 100,000 astronomical units or more, marking the edge of the Sun's gravitational dominance. At those distances, the Sun is just another star, not particularly bright or special looking. The objects in the Oort cloud orbit so slowly that they take millions of years to complete a single revolution. They're barely bound to the Sun at all. Other stars passing within a few light years can perturb their orbits, sending some inward, ejecting others into interstellar space. It's humbling to realize how much of our solar system is invisible. We think of the solar system as this orderly arrangement of planets and asteroid belts that we've mapped and photographed. But the truth is the vast majority of solar system objects are out there in the Oort cloud, unseen and unseeable, known only through theory and the occasional comet that falls inward and gives us a glimpse of what's waiting in the darkness. Maybe someday we'll send a probe out there, though the travel time would be measured in centuries or millennia with current technology. Maybe advanced telescopes will eventually be able to detect the faint reflected light from Oort cloud objects, confirming directly what we now know only indirectly. But for now, and probably for a long time to come, the Oort cloud remains theoretical, a structure we're confident exists because the math requires it, because the observations make sense only if it's there, but which remains perpetually beyond our direct perception. It's like knowing there's an ocean on the other side of the world because sometimes waves reach your shore, but never having actually seen that ocean yourself, never having sailed on it or mapped it or confirmed it exists beyond doubt. We see the comets, the waves, and we infer the source, and the inference is strong enough that scientists don't doubt the Oort cloud's existence. But still, it exists for us only as an idea, a model, a necessary hypothesis that explains the observations. 1 trillion comets waiting in darkness at the edge of everything, and not one of them directly visible, all of them known only through the few that occasionally fall inward and catch the light. Some comets orbit the Sun in the opposite direction from the planets. These are called retrograde comets, and they make up a significant fraction of the long-period comet population. While all the planets orbit counterclockwise as viewed from above Earth's North Pole, following the same general direction as the Sun's rotation, many comets don't care about that pattern. They come in from all angles, including orbits that go the wrong way around the Sun. This tells us something important about their origins. The planets all formed from the same disk of material orbiting the young Sun, and that disk had a particular direction of rotation, which everything in it inherited. But comets, especially those from the Oort cloud, were scattered outward during the solar system's early chaotic period by gravitational interactions with the giant planets, and when objects get scattered like that, thrown into extremely distant orbits by close encounters with Jupiter or Saturn or the other giants, the direction of their orbit becomes essentially random, so you get comets approaching the Sun from every direction. Some prograde, travelling the same direction as the planets, some retrograde, going the opposite way, some on highly inclined orbits that are neither prograde nor retrograde but somewhere in between. The Oort cloud is spherical because the scattering process that populated it didn't preserve the original disk structure. Objects were flung outward in all directions and their orbits randomized over time by stellar perturbations and galactic tides. When a retrograde comet passes through the inner solar system, it's travelling against the flow, so to speak. If it encounters a planet, the relative velocity is much higher than it would be for a prograde comet. You're adding the planet's orbital velocity to the comet's velocity rather than subtracting them. This makes retrograde comet encounters potentially more energetic, more dangerous if an impact were to occur. It also creates some beautiful dynamics. A retrograde comet's tail behaviour is the same, still pointing away from the Sun, but its motion across the sky can seem strange, moving backward relative to the planets and stars. Ancient astronomers tracking these objects would have noticed this retrograde motion and found it even more portentous than regular comets, of this visitor that not only appeared unexpectedly, but moved in opposition to the natural order. From the comet's perspective, if a comet could have a perspective, the direction doesn't matter. It's following the gravitational pull of the Sun, tracing out an ellipse or hyperbola defined purely by physics. Whether that path happens to be prograde or retrograde is almost incidental, a consequence of the particular perturbations that sent it inward. The comet doesn't know it's going the wrong way, doesn't experience its orbit as unusual. It's just falling toward the Sun and then climbing back out, same as every other comet, following the path that gravity dictates. But for us, trying to understand the structure and history of the solar system, these retrograde orbits are data points. They tell us about the violence of the early solar system, about how thoroughly the giant planets scattered material outward, about how the Oort cloud formed from debris rather than from orderly accretion. Every retrograde comet is evidence of ancient chaos, of a time when orbits were unstable and objects were being flung in all directions, creating the spherical cloud of distant comets we infer today from the angles at which they approach. In March 1996, Comet Hyakutake passed just 15 million kilometers from Earth, one of the closest comet approaches in 2 centuries. 15 million kilometers sounds like a vast distance, and it is, but in astronomical terms it's practically intimate. For comparison, the Moon orbits at about 384,000 kilometers, so Hyakutake passed at about 39 times the Moon's distance. Close enough that its tail stretched across 100 degrees of sky, so more than halfway from horizon to zenith, dominating the night for weeks. People in dark locations could see it easily with the naked eye, this fuzzy star with an enormous tail sweeping across constellations. Through binoculars it was spectacular. The coma resolved into detail, the tail showed structure, and on the best nights you could see both the dust tail and the ion tail diverging slightly as they streamed away from the nucleus. Amateur astronomers stayed up all night photographing it, capturing images that showed the tail extending past multiple constellations, literally too large to fit in most camera fields of view. What made Hyakutake particularly special was that it was unexpected. It had been discovered only 2 months before its close approach, found by an amateur astronomer in Japan, Yuji Hyakutake, who spotted it with large binoculars while comet hunting. Professional astronomers quickly calculated its orbit and realized it was going to pass very close to Earth, close enough to put on a spectacular show. And then everyone just had to wait, watching as this newly discovered comet grew brighter and closer, wondering exactly how impressive it would become. It delivered. For several weeks in late March and early April, Hyakutake was the dominant feature in the night sky for anyone with clear weather and dark skies. Its approach also allowed scientists to study a comet in detail that usually requires spacecraft. They could do spectroscopy, measure composition, track outgassing rates, observe the tail structure, all from Earth-based telescopes because the comet was so close. It was like having a natural laboratory approach us, near offering itself for examination. The comet's nucleus was small, only about 2 kilometers across, but at close range, even a small nucleus can create an impressive display. And Hyakutake was active, outgassing vigorously, creating that huge coma and long tail despite its modest size. It passed closest to Earth on March 25, 1996, and then continued on toward the Sun, where it reached perihelion in early May before heading back out into the solar system. We won't see it again for about 70,000 years. Its orbit is so elongated that the next return is in the distant future, long after everyone alive today is gone, long after our current civilization is dust. The comet will spend the next millennia climbing back out into the darkness, moving slower and slower as it reaches aphelion somewhere in the outer reaches of the Oort cloud. And then it will begin the long fall back inward, arriving in the inner solar system sometime around the year 72,000 CE, when whatever descendant species or civilization exists might look up and see this same comet making another close approach to Earth, completing an orbit that began in our time. For now, Hyakutake exists in photographs and memories, a reminder that sometimes the cosmos brings wonders close enough to see without telescopes, close enough to dominate the sky, close enough that people who normally never think about astronomy find themselves outside on cold March nights, looking up at this visitor from the edge of the solar system, this ancient object on a 70,000-year orbit that happened to pass through our neighborhood just when humans were around to notice and appreciate it. The ice in comets isn't just water ice. It includes frozen carbon dioxide, methane, ammonia, and a variety of other volatile compounds, each with its own sublimation temperature. This creates a kind of layered behavior as the comet approaches the Sun, with different ices becoming active at different distances, like a cosmic onion losing its layers one at a time as it warms. Carbon dioxide ice, for instance, sublimes at lower temperatures than water ice, which means it starts outgassing when the comet is still far from the Sun, perhaps beyond Jupiter's orbit. At those distances, water remains frozen, inert, but the CO2 is already turning to gas, creating early activity that might make the comet visible while it's still in the outer solar system. Then, as the comet continues inward and temperatures rise, water ice begins to sublime, re-adding its contribution to the outgassing, increasing the activity level dramatically. Methane, ammonia, carbon monoxide, each has its own threshold temperature, its own distance from the Sun where it transitions from solid to gas. This means a comet's behavior changes as it moves along its orbit, not just because it's getting more solar radiation, but because different chemical species are becoming active at different times. The composition of the coma changes, the colour might shift. The intensity of outgassing varies in ways that depend on the specific mixture of ices in that particular comet. It's like watching a clock with multiple hands, each moving at its own speed, each marking a different kind of time. The carbon dioxide hand starts moving early, the water ice hand starts later but becomes dominant. These other compounds add their own rhythms, their own contributions to the overall activity pattern. And all of this is happening because temperature is gradually increasing as the comet falls sunward, crossing threshold after threshold, activating layer after layer of frozen chemistry. This also means comets can have multiple peaks of activity. Maybe there's an early peak when carbon dioxide is most active, then activity might plateau or even decrease slightly as the comet continues inward. And then there's another peak, possibly larger, when water ice sublimation reaches its maximum rate near perihelion. The activity curve isn't a simple rise and fall, it's complex, multi-phased, reflecting the diversity of ices present in the nucleus. Scientists study these activity patterns to understand comet composition. Yes, by watching when different kinds of outgassing begin and end, they can infer what volatile compounds are present and in what proportions. A comet that becomes active very early, while still beyond Jupiter, probably has a lot of carbon monoxide or carbon dioxide, substances that sublime at low temperatures. A comet that remains inactive until it's closer to Mars probably has a composition dominated by water ice, and less of the more volatile compounds. And here's what makes it even more interesting. The ice distribution within the nucleus isn't uniform. One region might be rich in carbon dioxide, another might be mostly water ice, another might have a concentration of methane. As the nucleus rotates, different areas come into sunlight, and the composition of what's outgassing changes hour by hour. The comet is revealing its internal structure through the sequence and location of its outgassing, painting a picture of its composition one jet at a time. So when you watch a comet brighten as it approaches the sun, you're not just seeing it get warmer, you're watching a complex chemical performance unfold, with different ices taking their turns on stage, each contributing to the display according to its own properties, creating layers of activity that reflect the comet's formation history, the conditions in the early solar system where it accreted, the mixture of ices that happened to combine into this particular object billions of years ago. In late 2013, Comet Eason was being hailed as potentially the comet of the century, with predictions that it might become bright enough to see in daylight, rivaling the brightness of Venus or even the Moon. Astronomers and the public alike were watching eagerly as this Oort cloud visitor fell sunward on its first ever approach to the inner solar system, growing brighter, developing a tail, showing all the signs of becoming a spectacular display. The anticipation built for months. News outlets ran stories about when and where to see Eisen. Amateur astronomers prepared their equipment. NASA and other space agencies positioned spacecraft to observe the comet as it passed close to the sun. Everyone was ready for a show, for one of those once-in-a-lifetime events that gets remembered for decades, talked about by parents to children, marked in the collective memory as that year when the comet came. And then, as Eisen approached perihelion, passing just 1.2 million kilometers from the sun's surface on Thanksgiving Day 2013, something went wrong. Observatories watching the comet saw it begin to disintegrate. The nucleus broke apart under the intense tidal forces and heating, fragmenting into smaller pieces that continued to vaporize. Some small remnants emerged from perihelion briefly. There was a moment of hope that part of Eason had survived. But within days it was clear those remnants were also disintegrating, fading rapidly, disappearing into scattered dust. Ison was gone. The comet of the century had self-destructed, destroyed by the same solar encounter that was supposed to make it spectacular. Instead of a brilliant display visible to billions of people, we got a lesson in comet fragility, a reminder that these ancient objects are delicate, held together by weak forces, vulnerable to the extreme environment near the sun. The disappointment was palpable. Millions of people around the world had been looking forward to seeing this comet, had marked their calendars, had prepared to wake up early or stay up late to catch a glimpse. Instead, they got nothing. Or rather, they got the knowledge that sometimes astronomical predictions don't pan out, that comets can surprise us by failing to live up to expectations just as easily as they can surprise us by exceeding them. But there was something valuable in the failure too. Scientists learned about the structural limits of comet nuclei, about how close they can get to the sun before tidal forces and heating become fatal. The observations of Ison's disintegration provided data about how comets break apart, how quickly the fragments disperse. Now, what happens to the material when a nucleus is destroyed? It wasn't the show anyone wanted, but it was informative in its own way, and it served as a humbling reminder that nature doesn't perform on demand. We can predict orbits with exquisite precision. We knew exactly when and where Ison would pass the sun. But we can't predict whether a comet will hold together through that passage, whether its nucleus has the structural integrity to survive, whether it will become brilliant or disintegrate into nothing. Those factors depend on the comet's internal structure, its composition, its formation history, details we can't easily observe from Earth. So the comet of the century became the comet that wasn't, a lesson in managing expectations and accepting that the universe doesn't always give us the spectacles we hope for. Ison came from the Oort cloud, fell inward for millions of years, made its first and last approach to the sun, and scattered into dust and vapour, leaving behind only observations and a collective memory of anticipation that turned to disappointment. A reminder that even in astronomy, with all our predictive power, we're still at the mercy of forces and factors we can't fully control. When scientists analyze samples from comets and studied their spectra from Earth-based observations, they found something remarkable. Complex organic molecules, including glycine, the simplest amino acid. Not just carbon-based compounds or simple molecules, but actual amino acids, the building blocks of proteins, the fundamental components that living things use to construct the molecular machinery of life. This wasn't entirely unexpected. He'd given earlier discoveries, but each confirmation strengthens the case for a profound idea. The ingredients for life might not be unique to Earth, might not even have originated on Earth. They might be common throughout the universe, forming naturally in space through non-biological chemistry, getting incorporated into comets and asteroids, and then being delivered to planets during their formation and early bombardment phases. Think about what this means. The molecular components that allow for biology, that make consciousness possible, that let you read these words and think about their implications, those components might have formed in interstellar clouds or the early solar nebula long before Earth existed. They froze into comets, preserved in ice for billions of years, and eventually some fraction of them ended up here, delivered by impacts during Earth's early history. It's one of those discoveries that quietly rewrites how we think about life's origins. We used to imagine life emerging from purely terrestrial chemistry, from molecules formed in Earth's oceans or atmosphere through lightning or volcanic activity or whatever energy sources were available. And that probably happened too. But the comet finding suggests life had a head start, that some of the necessary ingredients were already present, already scattered across the young Earth by cosmic delivery, waiting to be incorporated into whatever chemical processes eventually led to the first self-replicating molecules. And if this happened on Earth, it likely happened elsewhere. Comets are universal. Every star system probably has them. Frozen objects in distant orbits carrying similar chemistry. If amino acids form naturally in space, if complex organics are a common product of cosmic chemistry, then these building blocks are probably raining down on planets around other stars too. The raw materials for life might be everywhere, scattered throughout galaxies, waiting for the right conditions to start doing something interesting. This doesn't mean life is inevitable, or that it's common. Getting from amino acids to actual living organisms is an enormous leap, requiring specific conditions and probably a great deal of chance. But it does mean the first step, having the necessary molecular components available, might not be the limiting factor we once thought it was. The universe might be far more ready for life than we assumed, might be providing the ingredients freely, leaving only the assembly process as the difficult part. So when you think about comets now, you're not just thinking about ice and dust and pretty tails, you're thinking about organic chemistry, about amino acids, about the building blocks of biology floating in space, preserved in frozen time capsules for billions of years, occasionally falling onto planets where they might contribute to something as improbable and magnificent as life itself. The comet that shines in the night sky might be carrying molecules structurally identical to ones in your cells, separated by billions of years of history, but united by the same cosmic chemistry that seems to operate everywhere matter exists. The Kuiper Belt contains a class of objects called centaurs, bodies that orbit in the region between Jupiter and Neptune and display characteristics of both asteroids and comets. Sometimes they look like asteroids, inert and inactive, just dark rocks following elliptical orbits. Other times they develop comae and tails behaving like comets, outgassing and creating activity that makes them clearly not just rocky bodies. These objects exist in a transitional zone, both literally and metaphorically. Their orbits place them between the realm of the asteroids and the realm of the comets, and their behavior reflects that in-between status. They're not as ice-rich as typical comets from the outer solar system, but they're not as ice-poor as asteroids from the main belt. There's something in the middle, and their behavior depends on their specific composition and their current orbital distance. A centaur might spend centuries appearing asteroidal, showing no activity, just drifting through space like any other rocky body. And then its orbit brings it slightly closer to the sun. Temperatures rise just enough and suddenly there's outgassing. A coma forms, maybe a tail develops. For a while it looks like a comet, acts like a comet, gets classified as an active comet. And then it moves farther away again, cools down, and the activity stops. It returns to looking like an asteroid. This transitional nature tells us something important about how we categorize solar system objects. We like to put things in boxes. This is an asteroid, this is a comet, these are the defining characteristics. But nature doesn't care about our categories. Nature creates a continuum, with pure asteroids on one end, pure comets on the other, and everything in between. The centaurs occupy that middle ground. reminding us that our classifications are human constructs imposed on a spectrum of objects that grade continuously from one type to another. Some centaurs are probably asteroids that captured some ice during formation or through collisions. Others are probably comets that have lost most but not all of their volatiles. Some might be objects that formed in place in the region they currently occupy, with compositions that naturally fall between the ice-rich outer solar system and the rock-rich inner solar system. We're still sorting out the details, still trying to understand the population's origins and evolution. What's clear is that the solar system's small bodies exist on a spectrum rather than in distinct categories. There's not a sharp dividing line where asteroids end and comets begin. There's a gradual transition, depopulated by objects like the centaurs that blur the boundaries, that challenge our attempts at clean classification, that show characteristics of both major groups depending on when and how you observe them. It's messy, which is perhaps fitting. The solar system formed through chaotic processes, collisions, migrations, scattering events. Why would we expect the resulting population of small bodies to fit neatly into human-defined categories? The centaurs, in their ambiguity, in their refusal to be purely one thing or another, might be more representative of solar system reality than the clear-cut examples we use to define our asteroid and comet categories. They're reminders that nature is continuous, that transitions exist between all our defined types, that the universe doesn't organize itself according to our taxonomies. The solar system contains asteroids and comets and everything in between, creating a rich population of objects whose properties and behaviors span the full range from rocky and inert to icy and active, with no sharp boundaries, just gradual transitions that sometimes produce objects that seem confused about what they're supposed to be. In January 2007, Comet McNaught became the brightest comet visible from Earth in over 40 years, briefly outshining even Venus, and becoming spectacular enough that people in the southern hemisphere could see it in broad daylight. Not at twilight, not against a darkening sky, but in the middle of the day, with the sun above the horizon, this comet was bright enough to be visible as a distinct object hanging in the blue sky. New reports came in from across the southern hemisphere of people spotting it during daytime. Observers in Australia, South Africa, South America, all seeing this fuzzy star that shouldn't be visible against the daylit sky. At night, for those lucky enough to have clear skies, McNaught was absolutely spectacular, with a tail that swept across huge portions of the sky, showing intricate structure, multiple streamers, fan-like features that changed from night to night as the comet moved and solar wind sculpted the tail. The comet reached perihelion on January 12, 2007, passing just 0.17 astronomical units from the Sun, closer than the orbit of Mercury, and at that point it was estimated to reach magnitude minus 5.5 or even brighter, rivaling Venus at its brightest. For a brief period, McNaught was one of the brightest objects in the sky apart from the Sun and Moon, visible without any optical aid, bright enough to cast faint shadows at night under ideal conditions. But it was the tail that really captured attention. As McNaught pulled away from the Sun and became more easily visible in dark skies, its tail extended across sometimes 30 or 40 degrees or more, showing this beautiful striped structure. Parallel streamers of dust, each one representing material released at slightly different times, each one following a slightly different trajectory as it got pushed by solar radiation pressure. The tail looked almost like a peacock's display, or a waterfall frozen in time, or rays of light spreading across the sky. Photographers around the southern hemisphere captured stunning images, some of the most beautiful comet photographs ever taken, showing McNaught's tail arcing over landscapes, spreading across twilight skies, creating scenes that looked almost too perfect to be real. For a few weeks in January 2007, if you were in the right hemisphere and had clear weather, you could witness a spectacle that only happens once or twice in a human lifetime. A truly great comet, bright enough to dominate the sky, beautiful enough to stop people in their tracks. And then it faded. McNaught continued its journey outward, cooling, becoming less active, its tail shortening and dimming. By February it required telescopes to see. By March it was gone from view entirely, heading back toward the outer solar system on an orbit that won't bring it back for thousands of years, if ever. The close solar passage might have altered its trajectory enough to eject it from the solar system entirely. For those who saw it, the McNaught remains a vivid memory, the comet that appeared in daylight, the tail that spread across the sky, the brief period when the cosmos decided to put on a show. For those who missed it due to geography or weather or simple bad luck, it remains a reminder that sometimes, rarely, comets actually do live up to the hype, actually do create the kind of displays that inspire awe and wonder, actually do justify all the anticipation and attention. McNaught delivered, and then it left, disappearing into the darkness like all comets eventually do, leaving behind only photographs and memories and the knowledge that yes, sometimes the universe creates beauty on a scale that matches our highest hopes. In November 2014, the European Space Agency achieved something unprecedented. They landed a spacecraft called Philae on a comet nucleus, and not just orbited it, not just flew past it, actually landed on it, touching down on the surface of Comet 67P/Churyumov-Gerasimenko while it was travelling through space at tens of thousands of kilometers per hour. It was the first time humanity had ever placed a probe on a comet, and the landing didn't go quite as planned, which somehow made it even more remarkable. Philae was supposed to fire harpoons into the surface upon landing, anchoring itself to the low-gravity nucleus so it wouldn't bounce off. But the harpoons didn't fire. When Philae touched down, moving at about walking speed relative to the comet, it bounced. In the incredibly weak gravity, about 100,000 times weaker than Earth's, that gentle touchdown was enough to send the lander back into space, tumbling slowly, rising hundreds of meters above the surface over the course of nearly 2 hours. And then it came down again, bounced a second time, smaller this time, and finally settled into a shadowed spot wedged against a cliff wall, tilted at an angle, with one of its 3 feet not even touching the ground. It was far from the intended landing site, oriented incorrectly, and most critically positioned where its solar panels couldn't receive enough sunlight to keep its batteries charged for long. But for about 60 hours before its batteries died, Philae worked. It drilled into the surface, or tried to. The drill didn't penetrate as deeply as hoped because the surface was harder than expected. It took photographs, showing a close-up view of the comet's terrain, this alien landscape of dust and boulders and strange formations. It measured the surface temperature, the composition, the density. It detected organic molecules in the dust. It provided data that scientists are still analysing years later, squeezing every bit of information from those 60 hours of operation. And then the batteries ran out, and Philae went silent. The Rosetta orbiter continued circling the comet, searching for the lander, trying to establish contact, hoping that as the comet's orbit brought it closer to the Sun, Philae's solar panels might receive enough light to wake up and transmit again. And eventually, months later, there was brief contact, a few sessions where Philae woke up, sent some data, and then went quiet again as shadows shifted and sunlight became intermittent. The mission ended in September 2016, when Rosetta itself was deliberately crashed into the comet's surface, adjoining Philae in permanent residence on 67P. Before impact, Rosetta's cameras finally spotted Philae in its resting place, wedged into that shadowed crevice, confirming what happened during those chaotic bounces, providing closure to the landing story. It wasn't the perfect mission execution anyone had hoped for, but it was real, messy, complicated. A reminder that space exploration is difficult, that landing on a rotating comet with almost no gravity is harder than it sounds, that sometimes things go wrong and you have to work with what you have, and what they had was still extraordinary. A lander on a comet, however briefly, however incompletely, providing data that had never been obtained before, touching the surface of an object that had never been touched, completing a journey that began years earlier when Rosetta launched from Earth. Philae is still there now, frozen in shadows on a comet that's heading back toward the outer solar system, its batteries long dead, its instruments silent, a human-made object accompanying 67P on its eternal orbit, a tiny monument to curiosity and ambition, and the willingness to try difficult things even when the outcome is uncertain. Scientists have measured the deuterium to hydrogen ratio in water from various comets, and here's what they found. Many comets have water with a significantly different isotopic signature than Earth's oceans. The ratio of heavy hydrogen, deuterium to regular hydrogen, is often about twice as high in cometary water compared to terrestrial water. This was surprising, and it complicated the story we told earlier about comets delivering Earth's oceans. Deuterium is just hydrogen with an extra neutron, still one proton, still hydrogen chemically, but heavier. Water molecules can incorporate deuterium instead of regular hydrogen, creating heavy water, D2O instead of H2O. The ratio of deuterium to hydrogen in water depends on where and how that water formed, preserving a kind of signature of its origin conditions. When that ratio doesn't match between cometary water and Earth's oceans, it suggests comets weren't the primary source of our water. Maybe they contributed some. The isotopic ratio in Earth's oceans could be a mixture from multiple sources, but if most of our water came from comets, we'd expect the ratios to match more closely. The discrepancy suggests we need to look elsewhere for the primary water delivery mechanism, most likely to water-rich asteroids from the outer main belt, which do show isotopic ratios closer to Earth's oceans. But here's where it gets interesting. Not all comets have the same deuterium ratio. Some match Earth's water quite well, others are very different. This variation suggests comets formed in different regions of the early solar system, under different temperature and chemical conditions, and were then scattered to their current locations. The deuterium ratio is like a birth certificate, preserving information about where in the solar nebula that particular comet's water froze. So instead of comets brought Earth's water being straightforwardly true or false, the answer is more nuanced. Some comets could have contributed water with the right isotopic signature, others couldn't, and the overall delivery of Earth's oceans probably involved multiple sources: comets, asteroids, maybe water that was incorporated into Earth during its formation, and somehow survived the heat of accretion. This is how science actually works, isn't it? The simple story gets complicated when you look closely at the data. What seemed like a clear answer, comets brought water, becomes uncertain when you measure isotopes and find they don't quite match. And then you have to build a more sophisticated model, one that includes multiple water sources, regional variations in the solar nebula, complex delivery mechanisms operating over millions of years. The truth, as usual, is messier than the headline. Comets probably did contribute some water to early Earth, but they weren't the only source, maybe not even the primary source, and the water they brought might have had a different isotopic composition than what ended up in our oceans. The full story involves asteroids and comets, and possibly indigenous water, all mixing together during Earth's violent youth, creating oceans whose isotopic signature reflects that complex history, preserving in the ratio of heavy to light hydrogen a record of where the water came from and how it arrived. Comets lose their tails when they're far from the sun, returning to being just dark, frozen nuclei drifting silently through space, and they regrow those tails each time they approach again. It's not a permanent feature, it's a temporary transformation that happens only when conditions are right. When solar radiation is strong enough to drive sublimation and create the outgassing that produces comas and tails. In the outer solar system, beyond Jupiter or Saturn, a comet is basically invisible. No tail, no coma, no activity. Just a small, dark object following its orbit, completely inert, indistinguishable from an asteroid except for its composition and orbital characteristics. The ice is frozen solid at those temperatures, with no sublimation occurring, nothing to create the spectacular displays we associate with comets. It's dormant, waiting. And then, as it falls inward and crosses some threshold distance, different for each comet depending on its composition, the transformation begins. First, maybe carbon dioxide ice starts subliming, creating early, faint activity. Then water ice joins in, and the coma grows, becomes more visible. The tail begins to form, initially small, then longer, sweeping away from the nucleus as solar wind and radiation pressure push the outgassing material. The comet wakes up, becomes active, transforms from dark nucleus to spectacular wanderer. This happens every orbit without fail, like a seasonal change but on a timescale of years or decades. Approach the sun, grow a tail, become bright and visible, move away from the sun, lose the tail, fade back into darkness. It's a cycle, repeated each time the comet completes its orbit. Each passage stripping away more material but also creating another display, another opportunity for observers to witness the transformation. Think about what this means for a short period comet, something that orbits the sun every few years. It goes through this cycle regularly, dormant, active, and dormant, active, like breathing, except each breath takes years and costs the comet some fraction of its mass. An old comet that's made hundreds of these cycles is weary, depleted, its activity growing fainter with each return as the easily sublimated ice gets used up and what remains becomes harder to access beneath the growing surface crust. But a fresh comet from the Oort cloud, making its first approach, has all its original volatiles intact. When it wakes up, it might do so spectacularly, erupting with activity, growing enormous tails, putting on shows that old, worn-out short-period comets can no longer manage. It's experiencing the transformation for the first time, and everything is fresh, reactive, ready to respond dramatically to the sun's warmth. The tail isn't the comet. It's just what the comet does when it's warm enough. But the real object is the nucleus, persistent, continuing through cycles of activity and dormancy, carrying the frozen record of its formation through orbit after orbit. The tails are temporary, beautiful, ephemeral features that appear and disappear according to the comet's distance from the sun, like flowers that bloom only under specific conditions and then withdraw, leaving the plant itself unchanged but diminished, waiting for the next season to bloom again. The Great Comet of 1577 played an unexpected role in the history of astronomy. It helped prove that comets orbit beyond the Moon, not in Earth's atmosphere as Aristotle had claimed 1500 years earlier. This might not sound revolutionary now, but at the time it was a fundamental challenge to accepted cosmology, undermining the idea that the heavens were perfect and unchanging, while everything temporary and chaotic happened only in the sublunary realm below the Moon. The astronomer who made this determination was Tycho Brahe, one of the most meticulous observers in the pre-telescope era. He measured the comet's position carefully from his observatory in Denmark, and he also collected observations from other astronomers across Europe. By comparing these measurements, a technique called parallax, he could determine the comet's distance. If it were in Earth's atmosphere, different observers would see it in noticeably different positions relative to the background stars. The closer the object, the larger the parallax. But the comet showed almost no parallax. Different observers, separated by hundreds of kilometers, saw it in essentially the same position against the stars. This meant it had to be far away, at least 4 times farther than the Moon, Tycho calculated, and therefore definitely beyond the lunar sphere, up in the realm of the heavens that Aristotelian cosmology claimed was eternal and unchanging. This was philosophically disturbing to many scholars. If comets existed in the celestial realm, then the heavens weren't unchanging. Things could appear and disappear up there. The perfect circular motions of the celestial spheres could be interrupted by these wandering objects following their own paths. The neat division between the temporary earthly realm and the eternal heavenly realm was breaking down. Tycho went further, thus showing that the comet's motion was best explained not by travelling through crystalline spheres, another Aristotelian concept, but by moving freely through space in what appeared to be an elliptical path around the Sun. This meant the crystalline spheres, if they existed, would have to be permeable, allowing comets to pass through them. Or maybe they didn't exist at all and space was simply empty, allowing objects to move through it freely. The observations of one comet, combined with careful measurement and geometric reasoning, began dismantling a worldview that had stood for over a millennium. It's one of those moments where astronomy becomes revolutionary, not by discovering something new, but by measuring something old more carefully and realizing the implications contradict what everyone has assumed was true. The Great Comet of 1577 faded and disappeared, continuing on its orbit, completely unaware that its passage had contributed to a scientific revolution. It was just following physics, just doing what comets do, but by appearing when it did, and being observed by someone as meticulous as Tycho Brahe, it helped change how humanity understood the structure of the cosmos, proving that the heavens were not as separate from Earth as ancient philosophy claimed, that temporary phenomena could occur beyond the Moon, that the universe was perhaps not organized according to human-designed principles of perfection and immutability. Some comets have been observed to split spontaneously, fragmenting into multiple pieces without any obvious external cause, no collision, no particularly close solar approach, no clear trigger. The nucleus just breaks apart, yes, sometimes into a few large pieces, sometimes into dozens of smaller fragments, each following a slightly different orbit, creating a family of related objects where there used to be one. We don't fully understand why this happens. The leading theories involve internal stress from rotation, thermal fractures caused by uneven heating, or structural weakness in the nucleus that finally gives way after thousands or millions of years. Remember, comet nuclei are incredibly fragile, held together by weak forces, often consisting of two or more lobes in contact. It might not take much to break them apart. Rapid rotation could do it. If jets spin the nucleus up too much, centrifugal forces might overcome the weak gravity and molecular forces holding the structure together. Or maybe thermal stress creates fractures, like ice cracking on a warming pond, and those fractures propagate until the nucleus breaks completely. Or perhaps the structure was always precarious, and some minor perturbation, a small impact, a particularly vigorous outburst, was the final straw. Whatever the cause, the results are observable. Where there was one comet, now there are multiple objects, each continuing along similar but slightly diverging orbits. Sometimes the fragments survive for years or decades, becoming distinct comets in their own right. Other times they're short-lived, quickly disintegrating further or evaporating entirely during their next solar approach. The Comets sun-grazer family, those comets we mentioned earlier that crash into the sun, probably all originated from a single large comet that broke up centuries or millennia ago, creating hundreds or thousands of fragments that now follow similar orbits, each making its own death dive toward the sun on a slightly different schedule. Every time Soho observes another Comets sun-grazer, it's watching another fragment from that ancient splitting event completing its final journey. Or consider Comet Biela, which split into two components in the 1840s. Both pieces returned as expected on the next orbit, still travelling together like binary companions. And then, on subsequent returns, they faded and eventually disappeared completely, never seen again. But Earth's orbit crosses Biela's former path, and when we do, we see meteor showers, the remnants of the comet, now just dust and small particles burning up in our atmosphere, creating the Andromedids. The comet split, disintegrated, and transformed into a stream of meteoric debris, completing the full life cycle from active comet to scattered dust. We're still learning what causes these spontaneous fragmentations, still trying to understand the internal structure and forces that make some comets resilient and others fragile. Each splitting event is a data point, another piece of information about how these objects are constructed, how they respond to stresses, what holds them together and what makes them fall apart. It's a reminder that comet nuclei aren't solid, stable objects. They're delicate aggregations, barely cohesive, sometimes literally held together by nothing more than ice and luck, waiting for the right conditions to break them into pieces that drift apart and continue their own separate journeys through the darkness. In August 2019, amateur astronomer Gennady Borisov spotted something unusual through his telescope in Crimea, a comet that wasn't gravitationally bound to our Sun. Its orbit was hyperbolic, meaning it was moving too fast to be captured. It was just passing through, a visitor from another star system. This was only the second interstellar object ever detected, following Oumuamua 2 years earlier, and it was the first one that was clearly, unmistakably a comet. Scientists around the world immediately turned their telescopes toward it, knowing they had only a limited window to observe this visitor from beyond before it left the solar system forever. And what they found was simultaneously thrilling and slightly anticlimactic. Comet Borisov looked normal. Remarkably, surprisingly normal. It had a coma, a tail, the right kind of outgassing for its distance from the sun. Spectroscopic analysis showed compositions similar to solar system comets: water ice, carbon monoxide, cyanide compounds, all the usual suspects. This was actually profound in its own way. Here was an object that formed around a different star, in a different stellar system, under potentially different conditions, and yet it was behaving almost exactly like our comets. The chemistry was similar, the structure seemed similar, the activity patterns matched what we'd expect from a solar system comet at that distance. It suggested that comet formation might be a universal process, that wherever planets form from protoplanetary disks, you get these same kinds of icy bodies in the outer regions. Borisov's trajectory meant it had been travelling through interstellar space for millions, much as possibly billions of years, ejected from its home system sometime in the distant past. Maybe during its star system's formation, when giant planets were migrating and scattering smaller bodies. Maybe from a gravitational interaction with a passing star. Whatever the cause, Borisov was flung outward, escaped its sun's gravity, and began a journey through the galaxy. And then, purely by chance, its path intersected our solar system. It fell inward past Jupiter, past Mars, swung around the Sun at a distance of about 2 astronomical units, roughly the orbit of the asteroid belt, and headed back out the way it came, never slowing enough to be captured, just briefly visiting before returning to interstellar space. The whole encounter from entry to exit took less than a year. We'll never see it again. Borisov is heading outward now, climbing out of the sun's gravitational well, returning to the darkness between stars where it spent most of its existence. In a few thousand years it'll be light years away, continuing through the galaxy, perhaps eventually encountering another star system where, if that system has astronomers, they might detect it briefly before it passes on. The discovery of Borisov and Oumuamua before it suggests these interstellar visitors might be common, that space between stars isn't completely empty, but contains objects ejected from countless star systems, wander in the galaxy, occasionally passing through systems like ours. Most probably go undetected. We only found Borisov because it was bright enough and close enough, and someone happened to be looking in the right direction at the right time. But the normality of it, the fact that an interstellar comet looks and behaves like our own comets, tells us something beautiful. The processes that created our solar system, that formed comets in the disk around the young sun, are probably operating everywhere. Other stars have comets too, following the same physics, made of similar materials behaving in similar ways. The universe, in its vastness, might be more uniform than we thought, not in everything, but in the basic processes of planetary system formation, creating similar objects around different stars, occasionally flinging them into the void where they become travellers between worlds, ambassadors from distant systems that most will never visit. The gas escaping from a comet's nucleus doesn't drift away gently. It erupts at speeds faster than sound, creating supersonic jets in the vacuum of space. When ice sublimates beneath the surface and gas builds up pressure, it eventually finds an outlet, a crack, a weak spot, a porous channel, and explodes outward at velocities that can reach several hundred meters per second, faster than the speed of sound in those same gases under normal atmospheric pressure. Of course, there's no atmosphere in space, so there's no sound to travel faster than. but the gas molecules are still moving at supersonic velocities, carrying dust and debris with them, creating these high-speed plumes that shoot away from the nucleus like natural rocket exhausts. These jets are what create the coma, what carry material into the tail, what push the nucleus around and change its rotation. They're the primary mechanism by which comets transform from frozen objects into active outgassing systems. When spacecraft observe these jets up close, they see structure, narrow streams, sometimes multiple jets from different locations, the flow changing as the nucleus rotates and different areas come into sunlight. The jets aren't continuous streams, they pulse, vary in intensity, turn on and off as surface conditions change. It's dynamic, chaotic, responsive to sunlight and rotation and the internal structure of the nucleus. The speeds involved mean that material ejected from the nucleus is moving fast enough to escape the comet's weak gravity easily. Even a small comet with escape velocity of just a few meters per second is no match for jets travelling at hundreds of meters per second. Once material gets into these supersonic flows, it's gone, off into space, becoming part of the coma, eventually making its way into the tail, and are never returning to the surface. This creates interesting dynamics when multiple jets are firing from different locations. The forces don't balance out perfectly. One side might be more active than the other, creating net thrust that pushes the nucleus, changing its trajectory, altering its rotation. The comet is essentially a spacecraft with dozens of uncontrolled thrusters firing based on which parts are in sunlight, creating accelerations that accumulate over time into measurable orbital changes. And here's something worth pausing on. Those gas molecules escaping at supersonic speeds are ancient. They've been locked in ice for 4.6 billion years, frozen in the darkness of the outer solar system, and now suddenly they're moving at hundreds of meters per second, exploding into space, experiencing freedom for the first time since they were incorporated into the comet during its formation. In less than a second, they go from frozen solid to supersonic gas, expanding into vacuum, dispersing into the vastness of space. The jets represent creation and destruction happening simultaneously. Creation of the coma and tail that make comets beautiful. Destruction of the nucleus that makes them temporary. Every molecule that escapes is one less molecule in the nucleus, one more contribution to the comet's eventual demise. The supersonic speeds ensure there's no going back, no recapture, no return. Once freed, the gas disperses, joins the solar wind, becomes part of the general interplanetary medium, its identity as comet material lost in the vastness of space. Long-period comets arriving from the Oort cloud carry with them something extraordinary. Records of gravitational disturbances from stars that passed near our solar system tens of thousands of years ago. Their orbits preserve a memory of those ancient stellar encounters, frozen in their trajectories like messages written in celestial mechanics, waiting to be decoded by astronomers who understand what they're seeing. When a star passes within a few light years of the solar system, which happens occasionally over astronomical timescales, its gravity can perturb objects in the Oort cloud, nudging them slightly, changing their orbits just enough to send some falling inward toward the sun. This process takes a long time. An object at 50,000 astronomical units, perturbed by a stellar encounter, might take 100,000 years or more to complete its fall inward, finally arriving in the inner solar system long after the star that disturbed it has moved on. So when we observe a long-period comet today, we're seeing the result of an event that might have occurred when Neanderthals still existed, or earlier, when human ancestors were just beginning to use stone tools. The star that sent this comet toward us has long since departed, continuing its orbit around the galaxy, but the comet remembers. Its trajectory encodes information about that encounter. The direction the star was moving, roughly how close it came, how strong its gravitational influence was. By studying the orbits of many long-period comets, astronomers can work backward, inferring when and where stellar encounters occurred, identifying which stars likely passed close to the Sun in the distant past. It's a form of archaeology, reading the historical record written in comet orbits, reconstructing events from epochs before human civilization existed. This also means we're constantly receiving comets sent toward us by stellar encounters from the distant past. The close approach of a star 50,000 years ago might still be releasing comets today, sending them inward in a slow, steady stream that will continue for thousands of years until that particular perturbation exhausts itself. And meanwhile, stars passing near the solar system today are perturbing other Oort cloud objects that won't arrive in the inner solar system until the distant future, long after our current civilization is gone. It creates this strange temporal layering, where effects from the distant past are still manifesting today, and causes happening now won't show effects for millennia to come. The Oort cloud acts as a kind of temporal buffer, storing gravitational information and releasing it slowly, creating a connection between different eras that spans tens or hundreds of thousands of years. When you see a long-period comet in the night sky, you're looking at something that was sent toward you by an event that occurred in the deep past, triggered by a star whose light reached Earth long ago, whose gravitational influence nudged an object in the Oort cloud and set in motion a journey that's only now reaching completion. The comet is a messenger from our solar system's own history, carrying news of an encounter that happened when Earth was in a different age, when the night sky looked different, when different species walked the planet, when everything about human society was unimaginably different from what it is today. We don't know exactly how many comets exist in the Oort cloud. The estimates are staggering and uncertain, ranging from hundreds of billions to several trillion objects. Several trillion. More comets than there are stars in many galaxies, all orbiting our Sun at such immense distances that they're completely invisible, known only through inference and statistical modelling. To understand what several trillion comets means, imagine this. If every star visible to the naked eye in the night sky were instead a comet in the Oort cloud, you'd still be accounting for less than 1% of the total population. The vast majority will never be seen, never detected, never studied. They'll orbit in the darkness until the sun dies, or until gravitational perturbations eject them into interstellar space, or until they're captured by a passing star billions of years from now. The total mass in the Oort cloud might exceed the mass of all the planets combined, though it's spread across such an enormous volume that the average density is essentially zero. If you were somehow teleported to a random location in the Oort cloud, the nearest comet might be millions of kilometers away. You'd see nothing but stars, the sun reduced to just another bright point of light, no indication that you were inside a massive cloud of frozen objects orbiting at the edge of the solar system's gravitational influence. This invisible population represents the largest reservoir of pristine material from the solar system's formation. Each comet is a time capsule. familiar, but there are so many time capsules that we could study comets for centuries and never sample more than a tiny fraction of the total population. The diversity must be enormous. Comets that formed in different regions of the early solar nebula at different times, under different conditions, all mixed together in this distant cloud. And here's what makes it even more remarkable. We might never know the true number. We can estimate based on the rate at which long-period comets arrive in the inner solar system, extrapolating backward to figure out how large a population would produce that arrival rate. But those estimates depend on assumptions about how often Oort cloud objects get perturbed, how many get ejected versus redirected inward, what fraction are large enough to become visible comets when they approach the Sun. The number could be on the lower end of estimates, maybe only a few 100 billion comets, only being relative here. Or it could be much higher, maybe 5 trillion, maybe 10 trillion, maybe we're off by an order of magnitude in either direction. Without being able to observe them directly, without being able to count them, we're left with educated guesses based on indirect evidence. So the Oort cloud remains mysterious in the most fundamental way. We don't even know how many objects it contains. We know it's vast. Know it's the largest structure associated with our solar system. Know it contains more frozen material than anywhere else in the Sun's domain. But the exact number, the precise population, remains uncertain, likely to remain uncertain until we develop technology capable of detecting objects that small and that dark at distances measured in tens of thousands of astronomical units. Several trillion comets, each one unique, each one carrying its own history, each one a potential visitor to the inner solar system, waiting in the darkness, orbiting slowly, taking millions of years to complete each revolution, preserving the chemistry and structure of the solar system's birth, ready to tell us their stories if we can catch them during their brief passage through our neighborhood. Every comet that visits the inner solar system is unique. No two have exactly the same composition, orbit, or behavior. This final fact might seem obvious, but sit with it for a moment, because it contains something profound about the nature of these objects and what they represent. Each comet formed in a specific location in the early solar nebula, accreting material from its local environment, incorporating whatever ice and dust happened to be available at that particular distance from the young Sun, at that particular moment in the disk's evolution. The composition reflects those formation conditions, the temperature, the available elements, the chemical processes that were operating in that region at that time. Then each comet experienced its own unique history. Maybe it was scattered outward early, flung into the Oort cloud during the first few million years, when giant planets were migrating and everything was chaotic. Or maybe it formed in the Kuiper belt and stayed there, and experiencing billions of years of relative stability punctuated by occasional gravitational perturbations. Or maybe it had close encounters with planets, multiple ejection attempts before finally being flung to the outer reaches, and each orbit is distinct. The specific ellipse or hyperbola it traces through space, determined by the sum of all gravitational interactions it's experienced, unique down to the smallest decimal places. The rotation rate, the rotation axis, the internal structure, the distribution of ice and dust within the nucleus, all different for every comet, all carrying the signature of that object's particular history. When a comet becomes active, it does so in its own way. The jets emerge from different locations, firing at different times with different intensities. The coma develops its own structure. The tail grows according to that comet's specific outgassing pattern and composition. No two look precisely alike, even if they're broadly similar, even if they follow the same general patterns. This uniqueness means every comet that appears is an opportunity to learn something new, to see a variation we haven't seen before, to measure a composition slightly different from any previous measurement, to observe behavior that challenges or refines our models. Even after studying thousands of comets, the next one will be different, will surprise us in some small or large way, will add another data point to our understanding of the diversity within this population. And each comet that visits carries its own story, where it formed, how it got to its current orbit, what stellar encounters or planetary gravitational assists shaped its trajectory, how much material it's lost on previous passes, how many more orbits it has before it's gone forever. These stories are written in composition and orbit and activity, waiting to be read by observers patient enough to watch, careful enough to measure, curious enough to wonder what this particular ancient object might teach us about the cosmos. So when you see a comet in the night sky, whether it's a bright, spectacular great comet or a faint smudge requiring a telescope, you're seeing something that has never existed before and will never exist again in quite that form. You're watching a unique object complete a unique journey, revealing itself to you during the brief period when it's warm enough and close enough to show what it's made of, what it's capable of, what secrets it carries from the solar system's distant past. Perhaps that's the most important thing to understand about comets. They're not interchangeable. They're individuals, each one carrying its own secrets, following its own path, contributing its own voice to the chorus of objects that populate our solar system. And every time one appears, we have the privilege of witnessing something that's simultaneously ancient and ephemeral, preserved for billions of years but actively destroying itself before our eyes, a reminder that the universe creates beauty through impermanence, meaning through uniqueness, and wonder through the simple fact that nothing, not even frozen chunks of ice from the edge of the solar system, is ever exactly repeated. And so we've drifted through 50 facts about comets, these wanderers from the edge of everything, all these messengers carrying frozen memories from the solar system's birth. We've watched them grow their tails and lose them again, seen them split apart and disappear, learned how they smell and how they behave and what they might mean for the origins of life itself. Perhaps what stays with you isn't any single fact, but the larger picture they create together, that the solar system is far stranger, far larger, far more dynamic than the simple model of planets orbiting the sun. That there are trillions of objects waiting in the darkness at the edge of the sun's influence, any one of which might someday fall inward and grace our skies with beauty. That the ingredients for life might be scattered throughout space, frozen in comets, waiting to seed new worlds. That even the most carefully predicted astronomical events can surprise us. That nature retains the capacity for unpredictability no matter how much we learn. Comets remind us that we're surrounded by ancient things, objects that formed before Earth existed, that carry chemistry from before biology, that preserve conditions from an era when our planet was just beginning to cool from its molten birth. They're time capsules and they're also messengers, telling us about stellar encounters from epochs before civilization, about the structure of the early solar system, about the processes that operate in protoplanetary disks around distant stars. And perhaps most importantly, they remind us that the universe still knows how to create beauty, that occasionally, without warning, The cosmos will send something bright enough to see with the naked eye, spectacular enough to stop people in their daily lives, memorable enough to be talked about for generations. These moments are rare. Most of us will see perhaps one or two truly great comets in our lifetimes, but they happen, will continue to happen, connecting us to everyone who's ever looked up and wondered at these strange visitors. The next great comet might be decades away, or it might appear next year, discovered by some amateur astronomer scanning the sky, its trajectory calculated to bring it into a spectacular display that captures the world's attention. We don't know when it will come, we just know that eventually one will. Because the Oort cloud is patient and full, and gravity is relentless, and stars pass near the solar system on their own orbits, nudging things, sending ancient objects on long journeys that eventually end in light. Until then, sleep well. And when you dream, maybe you'll dream of frozen objects in the darkness, of tales streaming across the night sky, of chemistry preserved from the beginning of everything, waiting in the cold and the quiet for its turn to fall sunward and shine. Good night,